बोला.
सरांशी तुम्ही बोललात का मोठं थँक्सचं?
नाही बोलू. पण ज्याला टाइम ठेवतोय बोलून घेऊ का? आणि समजा ते नाही तर लास्ट पॉईंट तर तू दे, ते मी दे आणि असं. पण वोट ऑफ थँक स्लाईड आहे ना, सर्व्हिसेस वी ऑफर असू. हां
हा,
नाही.
आहे आहे
हां ती तेव्हा दाखवायची.
आहे.
ते
ती
एनिवे.
2 सेशनच्या ब्रेकमध्ये पण आहे. योगेंद्र सरांची झाली ना प्रेझेंटेशन, त्याच्यानंतर खोसे सरांचं इंट्रोडक्शन आहे, जो काही मध्ये ब्रेक आहे इंट्रोडक्शन त्यामध्ये, तर तिथे ती स्लाइड आपण शो करतो.
ठीक आहे. नाही मग वोट ऑफ थँक्स काय करेल, प्रायझॉन आणि ऑल पार्टिसिपेट. योगेंद्र सिंग खोसे, प्रायझॉन अँड ऑल
ठीक
पार्टिसिपेट. बोलतो आनंतर
चालेल. हो
कारण की त्यांना सगळं पटवून देण्याचे काही कॉमेंट आलं नाही बोलतात.
हो हो.
आनंद ना. हा एक विषय बोलत राहिला मी सगळ्यात शेवटी वोट ऑफ थँक्स तू द्यावे तसं प्रपोज केलं, तुझी तयारी आहे ना त्याला? ठीक आहे. थँक्यू.
Hello. Hello, everyone. Am I audible to everyone?
Yes, ma'am. I can hear you.
Yes, yes.
Yes, you're audible.
Yes. So let's begin with webinar 150. Good afternoon, everyone. On behalf of EFC, Epicons Friends of Concrete, I, Rashmi Zarodev, webinar coordinator, warmly welcome all the participants for today's technical webinar 150 on the revised IS code 1893-2025. We are delighted to see the enthusiastic participation of professionals, faculty members, and students from across the country. Earthquake-resistant design is a critical aspect. Earthquake-resistant design is a critical aspect of structural engineering, especially in a country like India with a diverse seismic zones. With the release of revised IS 1893-2025, there are significant updates in seismic design philosophy, analysis procedure, code provisions, and seismic zones. These revisions call for a clear understanding not only of what has changed, but also why these changes are introduced and how they will influence building design practices. To address this important need, the EFC has organized this webinar to provide a comprehensive overview of the revised code through expert deliberations. We are privileged to have with us two eminent speakers who will bring both academic depth and practical insight to the subject. Our first speaker is Professor Dr. Yogindra Singh, a distinguished expert in earthquake engineering field. He will speak on seismic design of buildings by revised codes. Following this, we will have Dr. Vijay Khosi as an experienced structural engineering professional who will present on impact of IS 1893-2025 on design of buildings. We are confident that today's session will be highly informative and will contribute significantly to enhancing seismic design practice. We encourage all the participants to actively get engaged and take maximum benefit of this webinar. I must mention that the event is sponsored by Trizone MEP Solution Private Limited, Thane. Trizone one-step solution with more than 17 years of experience in the field. Trizone is rocking their way through the engineering services, specializing in HVAC and MEP contracting, with a particular focus on data centers, with highly skilled technical professionals, specialized skill set expert engineers as their foundation to offer you an efficient and economic design build engineering solution. Now, uh, I would request all the participants to please be mute and keep your cameras off throughout the session. Please put your question in question answer box, not in the chat box. Now, I would like to introduce our engineer, Jayan Kulkarni, founder, member, and managing director of Epicons Consultant Private Limited. He is B Civil from VJTI Mumbai 1976 and ME Structure VJTI Mumbai University 1970. His areas of interest are earthquake engineering, concrete mix design, codal provisions, advanced entity, seismic retrofitting, tall buildings, conservation of heritage structures, and Indian aesthetics. He is a technical administrative head of Epicons Consultant Private Limited. We have completed 9,000 projects till date. We have 5 branches: structural design, project management, consultancy, architecture, and detail engineering, assessment testing, and infra. Now, I would like to introduce our moderator of today's webinar is Engineer Anand Kulkarni, Director of Epicons Consultant Private Limited. He graduated with specialization in structures in 1897. He further pursued postgraduate studies in structures at SPC Mumbai. With 38 years of extensive experience in structural design, he also worked as a diverse range of projects, including residential, commercial, mall, hotel, and industrial buildings. His expertise lies in the design of tall buildings, having contributed to the structural engineering of over 80 tall buildings, ranging from 100 meter to 250 meter in height for leading developers. renowned for developing efficient structural systems and innovative design solutions. He is also a member of American Concrete Institute. Now I would like to introduce our next moderator, Engineer A.S. Baronikar. He is a MTech Structure 1990 from MS University, Baroda. He serves as a director of the company since 1999 and is a part of top management of the company. He is responsible for day-to-day management of two verticals of the company named Structural Unit, which handles structural design projects, and Specialized Scope and NDT Unit, which handles all the assignments related to structural assessment of existing structures, including seismic evaluation, analysis, and interpretation of NDT results, design and strengthening, retrofitting measures, and analysis of structures with special features. He is a member of Institute of Engineers as well as life member of Indian Society of Structural Engineers. He is also licensed practicing engineer registered in BMC and Thane Municipal Corporation. Now, Epicons Consultant Private Limited. As I said, we are specialized in designing high-rise buildings. So these are the charts we have achieved till date. Our speciality, our services in PMC and architecture. One of the major project is Metro Bhavan from MMRDA. This is inside. This is one of the biggest project we are handling right now. And these are some our NDT jobs till date. And it's our award and recognition. Our most prestigious award of Institute of Engineers, that Sanitary Industry Excellence Award 2019, and now 5 consecutive years we are receiving this award. Now I would like to invite Engineer Jayat Kulkarni to introduce EFC. So,
good afternoon. Am I audible? Fine.
Yes.
Okay.
Mr. Kulkarni,
So good afternoon, everybody. I welcome you all to your webinar 150 and brief background of EFC, Epicon Friends of Concrete. Next. EFC started organizing workshops from 17 September 99 to nearly 26 years back, which became platform for exchanging thoughts about latest developments in the field of civil and structural engineering, successfully conducted till today 88 workshops and 49 webinars. Next. Our thought leaders. Everything started with late Dr. P.C. Basu, Engineer A.B. Karnik, Engineer N.N. Shikhande. They were my bosses. We started earthquake engineering workshop with Dr. Murthy and Dr. Jain. And our today's leading professor or leading faculty is Professor Dr. Yogendra Singh. Next. At the same time, I am indebted to my professors from VGTI, Dr. V.N. Gupchip, Professor Sundaram, Professor M.G. Gadgil. He not only delivers the lecture, but also suggests the topic and supports the seminars. Of course, I am remembered of late Professor Dr. Jairam, under whom I had done my post-graduation in concrete technology. Next. Of course, our principal inspiration comes from friend, philosopher, and guru, late Engineer A.P. Remedios. Next. Normally, topics covered are codal provision, complex structural analysis and design, advanced concrete technology, deep foundation, construction chemical, waterproofing problems and solution, earthquake engineering, seismic retrofitting, and renewable energy. Next. Epicons Consultant is ISO 9001 2015 certified company, and one of our well-defined objective is imparting technical knowledge to the interested parties and society that we are following very religiously. Next. Today, we are at webinar 150. There are 2 different series. One is workshop, one is webinar. So this is on 30th January, that is today. And our next workshop is proposed to be on 28th February 2026, assessment, testing, and rehabilitation of bridges. Next. EFC team member, apart from myself, We have Anand Kulkarni, Anil Joshi, Ravindra Deshpande, P.P. Pandey, Parashar Muge, Arvind Parvekar, all unit heads and directors of Epicons. Everybody participates very actively in the workshops and webinar. Next. And with this, I thank you and hand over to Rashmi.
Thank you, sir. Now I would like to invite Engineer Arvind Parvekar, sir, to preamble webinar 150. Parvekar, sir. I think there is some technical issue. We will wait for a minute. Thank you.
One second, Mr. Bhalla. Sorry. Sorry, I was on mute. I'll just start again. Yeah. Friends, welcome to this webinar 150 on the revised IS 1893 2015 by Professor Dr. Yogendra Singh and Dr. Vijay Khose. I'm sure this subject doesn't need any preamble or introduction as such. We all know that the importance of this code, its significance in our day-to-day practice, and concerns related to its revision. I'm audible, I think, now, correct? Okay. Today's extraordinary large attendance proves that beyond any doubt. We have already crossed the registration of 500, and right now also there are around 275 people on there as attended. I'm sure rest will be joining. As all of you are aware, BIS has published the revised code in November 2025 for implementation and announced that the old code will be withdrawn in May 2025. So we are in the transition period now. Professor Dr. Yogendra Singh has been conducting physical workshops and webinars for AFC for many years now on the topics related to earthquake resistant design and related topics for us, including the codal provisions and logic behind the clauses. He had already conducted a full-day physical workshop on 24th and 25th November 2023 on the same codes when those were published as draft. Hence, we thought it prudent to organize an online lecture on the latest published revision of the code so that the industry can understand and comprehend the logic behind various clauses and changes expected in the designs of structure because of the same. As we understand, in this revision, there are major changes in the code which will substantially affect the working of designers. During this discussion, we are going to listen from him about the rationale of various important existing and proposed clauses, which is going to be treated as always. Today, he will also be joined by Dr. Vijay Khose, his distinguished disciple and himself a renowned structural engineer. So friends, without taking any more time further, I would like to hand over to Rashmi for the formal introduction of Professor Yogendra Singh. Thank you.
Thank you, sir. So let's start with our first speaker, Dr. Yogendra Singh. Dr. Yogendra Singh is a professor and former head, Department of Earthquake Engineering at IIT Roorkee. He obtained his B in Civil Engineering from IIT Roorkee in 1989 and MTech and PhD in Structural Engineering from IIT Delhi in 1990. I hope the screen is visible.
My screen is not
No,
visible.
screen
You
is
are
what,
audible, but
your
screen is
voice
not.
is audible, screen is not visible.
Just
No problem. You may go ahead. The screen is not important. So
Rashmi, you please go ahead.
go ahead.
okay, sir. Yes. So, Dr. Yogendra Singh is a professor for and former head of Department of Earthquake Engineering at IIT Roorkee. He is a MTech and PhD in Structural Engineering from IIT Delhi in 1990 and 1994. His research interest includes performance-based design of buildings and bridges, seismic vulnerabilities and risk evaluation, and earthquake engineering in hilly region. He has more than 30 years of research and technical teaching experience. He has served 2 terms of Indian Railway Bridge Engineering Chair. He has supervised 20 PhDs, published more than 100 research articles in referred journal, and presented 120 papers in conference. Now, I would like to hand over this to Dr. Yogendra Singh, sir, so that we can start our first session. Thank you.
Thank you very much, Ms. Rashmi. I hope I'm
Thank you,
audible,
sir.
and I
Yes,
will
sir, you are
share
audible.
my screen. And please confirm if my screen is visible. Is my screen visible?
Yes, sir.
Okay. So thank you very much, Epicons, for providing me this opportunity. And thank you all for joining in such large number. The topic is of great importance, the changes in IS 1893. So as you may be knowing by now that IS 1893 is going to have 11 parts, and out of those only 2 parts, part 1 and part 5, which are related to general seismic hazard and buildings. These have been published recently, and we will be talking about these 2 today. So my discussion will be in 2 parts. In the first part, I will talk about IS 1893 part 1, which is relatively longer because it contains many changes and many issues we have to discuss. And then the second part of my discussion will be related to IS 1893 part 5, which will be relatively smaller. And I will be focusing only on RCC buildings. So although our topic is general, but masonry and steel buildings, the code also covers those. I will not be covering today. Maybe sometime later we can talk about those if there is interest. So the first I am going to talk about is the changes in IS 1893 part 1. And in this part of the code, several new concepts have also been introduced. So there are changes. We will be talking about those changes, the rationale behind those changes. I hope I will be able to explain the rationale behind most of the changes, but there may be 1 or 2 points where I may not be able to explain the rationale. Maybe that will come later when the commentary to the code is published, and we will come to know what exactly goes behind those. But most of the things I will be able to explain. And then later on, Vijay has agreed to explain the impact of that on practical design. So in this IS 1893 part 1, the major changes have been listed in the foreword. I have taken from there only. So the first change is that the name of this part 1 has been changed. Earlier it was general provisions and buildings. Now it is general provisions. So this is not containing specific clauses regarding buildings. It is giving hazard related clauses related to all structures. So that is part 1. And then as we know, and the main highlight of this change is the revised earthquake zonation map. And this earthquake zonation map is based on probabilistic earthquake hazard assessment. The previous maps, which were continuing in up to IS 1893-2016, though that map was based on deterministic seismic hazard assessment. So we will also talk a little bit about the difference between probabilistic and deterministic and how these two can be correlated. Then the design response spectrum has been now given up to 10 seconds. Earlier it was given up to 4 seconds in earlier code versions. Then in 2016 it was given up to 6 seconds, and then now it has been given up to 10 seconds. And the shape of the response spectrum has also been modified. We will discuss that. The design horizontal acceleration coefficients is specified for each zone corresponding to different return periods are given. So one major change which has been done this time is that the importance factor and the load factor have been included in the zone factor itself. And the zone factor accordingly corresponding to different importance factors, it is now defined for different return periods. So I will also try to explain what is the relationship between different return periods and the corresponding importance factor if it was expressed in terms of importance factor. Then the code has this time focused on time history analysis, and suits of far field ground motions are provided. So for different zones, standard ground motion suits are also provided. At the moment, only the ground motion nomenclature has been published. Soon, the actual ground motions will also be available on BIS websites. They are trying to arrange space to provide the links for that. Then a method for soil flexibility has been included, and the code emphasizes on the soil flexibility effect on different structures. And our focus will be on buildings. Then the method to estimate liquefaction potential has been revised. So some changes are there. And the clause on protection of architectural elements and utilities is introduced. This is also a new addition, because earlier code was talking about only structural components. But we know in case of earthquake, it is not only the structural components, the non-structural components and contents and services, those are also very important. So this code caters to the protection of architectural elements and utilities as well. So the philosophy of the earthquake resistant design in our code, that remains same. And this philosophy, just to revise, we all know that we try to estimate the hazard as realistically as possible. Then we divide the hazard by a response reduction factor. We reduce the hazard, and then we design for this reduced hazard. And we are following either working stress method or limit state method with the reduced hazard. And as a result, there is some overstrength. So some hidden strength available in our structure because of the factors of safety and the definition of characteristic strength used in limit state method. And in case of working stress method, we have a direct factor of safety. So due to that, there is some hidden strength. And then at many times, we have some subjective overstrength. The designers tend to provide strength more than required. So all that together makes the actual strength of the building higher, but still it is much less than the earthquake force which will be applied on the building or the structure. So we design for reduced forces, assuming that the hidden strength and the ductility together will be able to take care of the actual earthquake force, actual earthquake action, which is much stronger than what we are designing for. And the difference of this current design philosophy with performance-based design is that in performance-based design, we try to estimate the actual behavior using nonlinear analysis. Our code, including this 2025 revision, it is based on linear analysis. And as a result, the effect of inelasticity is considered indirectly through this response reduction factor. And the response reduction factors remain more or less same. Only a few new structural systems have been added, and response reduction factors for those have been provided. That's it. Otherwise, this concept of response reduction factor and the philosophy of earthquake resistant design, that remains more or less same. Now coming to the earthquake or seismic hazard. So any earthquake is represented by its signature. So this signature is nothing but accelerogram, this which is record of an accelerograph. So it is giving us the plot of acceleration at a point with time, and this is characteristic of any earthquake. Any earthquake can be represented by this, and this is like a random function which is changing its direction randomly in a fraction of second. And if we integrate the acceleration, we will get velocity, which can also be obtained by direct measurement from a seismograph, and the record is called seismogram. And if we integrate once or more this velocity record, we will get the displacement. So these three types of time histories are important to us. The acceleration time history, velocity and displacement time histories can be obtained by integration and double integration of acceleration time history. Now the question which faces us and which all the codes are trying to answer is that which earthquake we should design for. These signatures, accelerograms of each earthquake are unique. None of those accelerograms which we have recorded so far will be repeated in future. The future earthquakes are going to cause, even if those are caused on the same site and originating from the same source, even then their signatures are going to be different. Their accelerograms are going to be different. Then this question remains that which earthquake we should design for. And the answer is not easy. To find the answer, we try to understand what are the different characteristics of these ground motion records. So three major characteristics: the amplitude of shaking, which is represented in terms of PGA, PGB, and PGD, and the zone factor is actually representing this peak ground acceleration. So it is a measure of this peak ground acceleration which we expect in a zone or at a site. So this is one important characteristic. Another important characteristic is the frequency content. So this frequency content of different ground motions is different, and depending upon the coincidence or the proximity of the frequency of vibration of our structure with the frequency content of the ground motion, the response of the structure varies a lot. And this is considered through the shape of the response spectrum in the codes. Then duration of earthquake is also important. Currently, with linear analysis, the effect of the duration cannot be accounted for. So our current design philosophy takes into account only these first two characteristics, amplitude and frequency. The duration effect can be taken into account through nonlinear analysis only. So currently our codes are based on an average duration and the degradation of structure under that duration. Now the parameters which are affecting a ground motion, there are three parameters: the source effect, so which type of fault rupture is taking place, which type of slip it is occurring, and whether that fault is near to the fault, what we call near fault or near field effect, or it is away, sufficiently away from the fault, or what we call far field. Then path effects, when the energy released at the focus travels to the structure, the path it is taking, it is getting affected by whole of that path, including its distance, characteristics, different layers, different types of rock available in that path. So that also affects. And the local site effects. So site effects, that is the soil deposits mostly, which are affecting the earthquake ground motion at any site. Now together these characteristics can be represented, except duration, the amplitude and frequency content can be represented by the response spectrum, and perhaps all of us know the definition of response spectrum, which is a plot of peak response of single degree freedom systems. So response spectrum is giving the response of a simple structure. That simple structure can be represented by a single degree of freedom system. So that simple structure response we can read directly from the response spectrum. And what is given in our code is an idealized shape. The response spectrum for individual ground motion is quite zigzag, but when we consider a large number of ground motions, we can get a smooth curve given like in our codes. Now, in response spectrum, these three ranges are important. Here you see between TA and TV, this is constant acceleration range, or what we call acceleration controlled range or acceleration sensitive range. So in this range, the if the period of the structure lies within this range, TA to TV, the acceleration of the structure will be constant. Now, from the acceleration response spectrum, we can generate velocity response spectrum, simply dividing it by omega. This omega is nothing but angular frequency. So if we divide it by angular frequency, we will get the velocity of that single degree freedom system. And we can see that from TB to TC, it is the velocity which is constant. And similarly, we can also convert this into displacement spectrum by dividing the acceleration spectrum by omega square. So then the shape of the displacement spectrum is like this. And it is interesting to compare the shape of the acceleration spectrum with the displacement spectrum. So we can see between TV or beyond TV, we can see that as the period increases, the acceleration reduces. So except in this very short period range up to TA, and value of TA is close to 0.1 second. So from 0 to 0.1 second, and very few structures, none of the buildings will have the period in this range, fundamental period in this range. Only higher mode, some higher mode periods can come in this range. So except this range, the acceleration is either constant or it is decreasing. But if we look at the displacement spectrum, the displacement of the single degree freedom system, that simple structure continuously increases up to TC, and it becomes constant beyond TC. So this tells us that what effect the flexibility of the structure will have on its acceleration response and displacement response. Whereas the acceleration response reduces with increasing flexibility of the building, the displacement response increases with increasing flexibility of the structure. So this shape of the response spectrum, we are all familiar, and this is existing in our previous code, now previous code, 2016 version. So we can see up to 4 seconds, it is similar to what I have shown here, but beyond 4 seconds, this 4 seconds is something like TC. Beyond TC, the shape is erroneous. Why it is erroneous? Because in reality, it should be proportional to 1 upon t square, because if it is proportional to 1 upon t square, then only we are going to get the displacement constant, which is observed beyond this period TC. But our current code was having this acceleration, spectral acceleration constant beyond 4 seconds. And that was leading to erroneous calculation of the displacement for flexible structures like tall buildings. So this has been corrected in the revised code. I have intentionally not shown from 2025 code because this figure was published in the 2023 white circulation code, and it is more illustrative. That's why I have taken that. So up to 0 to 0.01 second, that means very, very rigid structures, which are considered to be infinitely rigid. The acceleration is same as what we call effective peak ground acceleration. So effective PGA is the acceleration of the rigid structure. Beyond 0.01 second up to 0.1 second, the response of the structure increases, the acceleration response of the structure increases linearly, and beyond 0.1 second, it becomes constant up to what we call a corner period TB. So that is the corner period, or the period at the junction of acceleration control and velocity control range. Beyond that, the acceleration response is proportional to 1 upon t, so it reduces inversely proportional to t. And up to 6 seconds, this inversely proportional or velocity controlled range continues, and beyond 6 seconds, it is proportional to 1 upon t square. And now the code defines all the three ranges properly. So acceleration controlled range, velocity controlled range, and displacement controlled range, which was not properly defined in the previous code. So we should understand some relationships. So what our code is giving as acceleration response spectrum, we have to understand that it is not really the acceleration. it is what we call pseudo acceleration or spectral acceleration. Pseudo acceleration is nothing but omega square times d. So d is the maximum displacement of this single degree freedom system. If we multiply it by omega square, then it becomes close and similar to acceleration. So you can see the units, d is having the units of meter, omega square is radian per second whole square. So it becomes meter per second square. That is same as the unit of acceleration. And it behaves like acceleration because if you multiply this omega square d by the mass, it will give the stiffness force. It will not give us the inertia force. So the difference between the real acceleration u double dot and pseudo acceleration omega square d is that if you multiply u double dot with mass, you will get the inertia force. If you multiply omega square d with mass, you will get the stiffness force or the forces in the column or stories or the structure. So we are more interested in the column forces or member forces. So those that member forces is given by k into u or m into omega square d. So that force we are interested in. That's why all the codes provide pseudo acceleration spectrum, not the real acceleration spectrum. Actually, real acceleration is not that useful to us as the pseudo acceleration. And similarly, the pseudo velocity is also defined as omega times d, and the relationship between acceleration, pseudo velocity, and displacement. So this displacement is real. So displacement is real, but acceleration and velocities are pseudo. If the structure is undamped, then the pseudo velocity and pseudo acceleration is equal to the acceleration, real acceleration of the single degree freedom system or structure. But if damping is there, then slight difference is created. Depending upon how much damping is there, the difference will increase. But usually the damping in our structures is much less. We know less than 5% or 10%, not more than that. So for that range, the pseudo acceleration and real accelerations are very close. So these relationships are also incorporated in IS 1893 part 1 revised 225. So we can first get the velocity if we know the acceleration. So that is multiplied by t over 2 pi. That is nothing but 1 by omega. Omega is 2 pi by t. So if you multiply acceleration or divide acceleration by omega, you will get velocity. It is there in horizontal direction as well as in vertical direction. And the displacement can be obtained by dividing acceleration by omega square. So these relations are incorporated in our 2025 code. The shape of the response spectrum is like this. Using these relationships, it can be converted into velocity control range. So earlier I have shown the same response spectrum, but in a schematic manner. Here I have plotted to the scale. So if you plot to the scale, it will look like this, that most of this range is velocity control, and most of our structures will lie in velocity control range, where the spectral acceleration is proportional to 1 upon t. And the displacement spectrum will look like this. Beyond 6 seconds, the displacement will be constant. Now, another term which our code has included is far field and near field effects. So what is far field and near field? The code defines near field, and then it defines far field as those motions which do not have the near field effect. So what is this near field effect or near fault effect? We should understand. So when our site is very close to the source of the earthquake, then the ground motion has certain characteristics. Those characteristics are predominantly described as pulse-like ground motion. So what is this pulse-like ground motion? That a velocity pulse is included in the ground motion. And that velocity pulse, as I said, that the velocity is nothing but integral of the acceleration. So acceleration is such that if you integrate it, you will see in the velocity record a pulse. And the velocity is representing the energy input to the structure. So the energy input to the structure is higher because of this velocity pulse. And as a result, for the same value of PGA, the structures in near field are subjected to near fault effect or near field ground motion, which is having velocity pulse, it will be subjected to more damage. But we have to understand that not all the ground motions in near field or near fault region have pulse-like motion. So only few ground motions in few certain conditions, this type of ground motion is observed. So what is that condition? We will discuss. And another issue which occurs in case of near field ground motion is directivity. So by directivity, it is meant that we get stronger component along any one direction, and the component in the other direction is weaker. So generally, when we are recording the earthquakes, we are placing our seismograph in north, south, east, west direction. So it will record the component in north, south direction and east, west direction. But it's not necessary that the strongest earthquake motion occurs in one of those two directions. So that can occur at any angle. Now, if we are measuring two components at or in orthogonal directions, then we know we can get or we can resolve any vector into these two orthogonal directions. So whichever direction of earthquake is strongest, we will be able to record by having orthogonal records in any two directions. Conventionally, that is north, south, and east, west. But this is true for ground motion. We can do it for ground motion. So if I record ground motion components in north, south, and east, west direction, I can generate ground motion components at any angle. And from that, I will come to know that in which direction I am getting the maximum intensity. Now, what is shown here in this slide is record of a single degree freedom system subjected to two horizontal components of the same ground motion. So one ground motion, this HWA03I, and this is recording from Chichi earthquake, and another this Glory array number 6, which is from Morgan Hill 1984 earthquake. And this is the response in horizontal plane. So we can see that the single degree freedom system is not vibrating in any one direction, it is vibrating in all the directions. And for this Chichi earthquake, the vibrations in all the directions are more or less of same peak amplitude. So peak amplitude in all the directions is more or less same. So this is a typical far field ground motion or the ground motion not having directivity. Whereas this Morgan Hill earthquake ground motion, you can see that the ground motion or the response of the single degree freedom system, which is representing the intensity of the ground motion, is stronger in one direction and much weaker in the other direction. So this type of ground motion we call as polarized ground motion, or the ground motion having a stronger component along one direction and weaker component on the other direction. Generally in near field, we experience this type of behavior of the ground motion, which is stronger along one direction. Now, the question is that when we are developing response spectrum can be developed for one component only. So any one component of ground motion, we can develop the response spectrum. We cannot develop response spectrum for two components simultaneously. So what we do, we generate response spectra for ground motion components at different angles. So we have measured along north, south, east, west only, but we can generate the ground motions by taking components at any direction. So we develop the ground motion records in different directions and then plot the response spectra for all those ground motions. And if we plot the response spectra of all those ground motions, the response spectra are going to vary. And those are not only going to vary with respect to the directions, those are also going to vary with respect to the period. So maybe at one period, one direction is giving us the maximum response. At another period, some other direction is giving us the peak response. So if I make an ensemble of these response spectra and then take either median or 84 percentile or envelope. Then accordingly, these response spectra are called SA ROT D100. So SA ROT D100 means the maximum in any direction. So this is giving us the maximum response spectrum. So similarly, we can get the minimum, that will be ROT 0. We can get median. So median is ROT D50. Currently, our code in AC7 also it is ROT D100. Our code also has ROT D100 response spectrum. So the envelope of all directions is considered. This is a new concept which is used. It is unclear in the previous code whether any such definition was used or not. Then another effect is the directionality effect. So if you consider the direction of ROT D100 from any one direction, north, south, or from the strike direction of the earthquake. So strike direction is the direction along which the fault rupture takes place. So the horizontal projection of that plane, that line is called the strike direction, along which the rupture is propagating at the surface. So if we take the ROT D100 direction from there and take the plot, so we can see in the near field direction, maximum probability is of this ROT D100 component being at 90 degree, perpendicular to the strike direction. So maximum component occurs along that. So this is called the directionality or the direction of the peak response. Now, the other effect we can understand which occurs because of the propagation of rupture. So rupture in a typical earthquake, large magnitude earthquake, let us say 8 magnitude earthquake, the rupture length is several hundred kilometers, 250 kilometers, 300 kilometers. So that is the distance. And that 250 kilometer rupture does not occur simultaneously. It starts from one point and then it progresses. So this depth of the movement of the rupture, the velocity of movement of the rupture with respect to the velocity of the elastic waves which are traveling from each rupture point, that also defines the characteristics of the ground motion. It is similar to Doppler effect, which we have learned in sound. So we can see here if this 0 is the initial location when the energy is released. So the wavefront is shown by the circle, and then when the energy is released at the next time step, then the circle is shown here. So we can see that if I sum up or I look the energy at the left point, then I will get this type of arrival of waves. On the right side, I will get this type of arrival of the wave. And we can see that because of the coincidence of the waves reaching from different sources, the pulses reaching from different sources or different points, this energy will be summed up. There will be constructive interference, or there will be addition of energy, and this will result in high energy pulse. That is called flange or velocity pulse. So this is the typical earthquake. The accelerogram is somewhat similar to what we usually see, but when we convert it into velocity, when we integrate it, then we see here, we see a large velocity. And if we convert into displacement, then we see that at this time where this velocity pulse is occurring, there is a significant displacement occurring in one direction. So because of this large displacement occurring in one direction, we have this velocity pulse getting generated. And this type of pulse will input much larger energy to our structure. So two effects in near field are there. One is this fling, which is velocity pulse, or another effect is the directivity, the strong direction of the ground motion or direction of the strong ground motion. So strong ground motion direction is perpendicular to the fault. So this is the strike direction along which the motion or rupture is taking place. Perpendicular to this, that is the direction of strong ground motion or ROT D100. So this is directionality. And if we know, if in some situation there is a well-defined fault, well-known fault, and we can define perpendicular direction of this, then we understand that this direction of the building will be subjected to stronger earthquake, and the perpendicular direction of the building will be subjected to smaller or lower intensity earthquake. But in the perpendicular direction, we are going to get this fling along the direction of the fault. If any building happens in the same direction, that will be subjected to this fling. So these effects are identified by the code, the revised code, although still it does not provide means to handle these, but these have been recognized. And in future, when our attenuation relationships will develop further, in future revisions, this will be the direction where near field effects will be considered. Currently, the code is based on far field ground motions because most of the records available are in far field. Based on that, the attenuation relationships have also been developed in far field, and the response spectra which is available in the code and the ground motions which are provided in the annexure, those are in the far field. Now, spatial variation of the ground motion has also been recognized. We understand that when the ground motion waves, seismic waves, are traveling from the source to the site, those waves are reaching after a certain time. So those take some time to travel. So between 2 points which have some distance, the waves will take different time interval to reach there, or there will be slight difference in the ground motion reaching at 2 points. So the code recognizes this effect also, and it says that if the footprint of the structure, and that is true in case of our buildings, so if the footprint is smaller, then we need not to consider this spatial variation. But if the footprint is large, and when we say smaller or larger in comparison to the wavelength of that ground motion, so like if we have a long span cable stayed bridge, so there the footprint of the structure is much larger, there we need to consider spatial ground motion. So variation of the ground motion below different supports, different pylons, we need to consider there. So this is also recognized by the code. Again, the code currently is not providing procedure how to consider it, but IRC code, IRCSP 114 has the procedure to consider this spatial variation. So if anybody is interested in using spatial variation, or you come across a structure which is having long lengths, something like 500 meter, depending upon the type of the soil, that length will vary. So 300 to 500 meter or larger, and if that is the size of the footprint, then we need to consider the non-uniform ground motion. Then the major change which has occurred in this revision is probabilistic seismic hazard assessment. So two methods are available for seismic hazard assessment in literature: deterministic seismic hazard assessment and probabilistic seismic hazard assessment. In deterministic seismic hazard assessment, the source characteristics, the path characteristics, and site are considered deterministically. Means that we are considering a most unfavorable scenario. So the maximum earthquake which we expect at a particular site, that we are getting from deterministic seismic hazard assessment. Now, as a result of deterministic seismic hazard assessment also, we get either a median or average, or mean plus 1 sigma, or mean minus 1 sigma value. What is available in our code till 2016 version is median value or mean value of the response spectrum, which is obtained from deterministic seismic hazard assessment. This we have to keep in mind. Now, in probabilistic seismic hazard assessment, as the name itself suggests, variability in estimation of all these parameters is considered. For example, one important parameter is the fault rupture length, which is going to rupture in future earthquake. So that cannot be estimated precisely. So that's why in case of deterministic seismic hazard assessment, we are considering the maximum possible length. But in reality, there are different possibilities. Different lengths can rupture at a time. So if we take those uncertainties in source characteristics, path characteristics, and site characteristics, and combine them together to get the seismic hazard assessment in the process of seismic hazard assessment, then we will get different probabilities of occurrence of different earthquake levels. Different intensity levels will have different probabilities of occurrence. So in case of deterministic seismic hazard assessment, the steps are like this, that first we consider all active faults in the vicinity of the structure, and that we mean, by vicinity we mean within a radius of 300 kilometers. Then we calculate the largest earthquake that could happen on these faults, generally based on the rupture length of the fault, which is possible. We can also consider the earthquakes which have occurred in past on that fault, if any information is available. And then we estimate the largest hazard caused by these different sources. So that we call governing. And that governing earthquake we can use in our design. Now, more than one governing earthquakes are possible. In one period range, one source is governing, whereas in another period range, another source is governing. That is possible. So in such situations, we take envelope of the two response spectra, which are governing in different period ranges. Graphically, that procedure is explained in this slide. The three steps. In first step, we identify different sources. Then we consider distances or the path characteristics, and then we use the attenuation relationships. And from those attenuation relationships, we get the intensity measure, estimate of the intensity measure, or response spectrum, we can say. So we get the response spectra, and these attenuation relationships which we are using, these have been obtained from regression in past earthquake data. So these can provide us median 84 percentile or any percentile value, or mean plus some fraction of sigma that we can use. Commonly used value is 84 percentile and median. So 84 percentile value is, I will show later, is considered equivalent to MC. Now, how the magnitude is computed, this is one example. This Welsh and Copper-Smith relationship, where magnitude is based on length or area or displacement. Generally, we have the information about length, possible length of rupture only. The actual fault plane is hidden inside the Earth's surface, so it is difficult to obtain. And how much displacement will occur, that is even more difficult. But based on the past earthquake records, these empirical relations have been developed, and many cases this or similar empirical relationships are used. So the code IS 1893 Part 1 2025, it has identified different sources and list of those sources. So this is the map showing different sources. Total 32 or 33 sources are identified, and the corresponding magnitude, which is considered in probabilistic seismic hazard assessment and deterministic seismic hazard assessment. Our code is calling probabilistic earthquake hazard assessment, PEHA and DEHA. In literature, more commonly it is used as PSHA and DSHA, probabilistic seismic hazard assessment and deterministic seismic hazard assessment. So what maximum magnitude which is possible at these faults, that is given. This information was not available in the previous code. So here, if we know the site coordinates, longitude and latitudes, we can see that what magnitude earthquakes can be generated in the vicinity of that site. So for all the 33 source zones, the maximum possible magnitudes are defined and are available in the code. So in probabilistic seismic hazard assessment, we take into account the variability in different, or uncertainty in different steps, and we combine that in statistical analysis. And using statistical analysis, we get a distribution. We fit a normal distribution, rather log normal distribution, and then we get the hazard curves. And from those hazard curves, we can develop the uniform hazard response spectrum. So uniform hazard response spectrum is nothing but a response spectrum which has uniform probability of accidents corresponding to each period. So if we plot hazard curves for different probability of occurrence, and then take the values corresponding to different periods and plot them, we will get what we call UHS. So what is given in our code is UHS, uniform hazard spectrum. And each uniform hazard spectrum has the characteristic probability of accidents, which is generally in terms of lifespan of the structure, design life, that is 50 years. So 50% in 50 years, 20% in 50 years, 10% in 50 years, 5% in 50 years, or so on. ASTO code, which is actually for bridges, that is also using something like 7% in 75 years. And this is nothing but this comes out to be close to 5% in 50 years. So 5% in 50 years will be actually 7.5% in 75 years. So they are considering 7%. Now, this probability of accidents can also be expressed in terms of mean return period. So 50% in 50 years is having a mean return period of 72 years. 10% in 50 years, this is very commonly used. This is also called design basis earthquake, whereas 50% in 50 years or 75 years return period, that is usually called serviceability earthquake, and 2% in 50 years, that is called MCE. Conventionally, or till 2025, our code or our design was based on this DBE, design basis earthquake, for 75 years return period. And other codes like AC7 or Eurocode, those are also using these. And if the building is designed for this DBE, it will be suffering some damage at this earthquake also, and it will be subjected to severe damage at higher earthquakes as well. So those buildings in which we want to reduce the damage, we were designing with importance factor. Now in the current code, in the revised code, that importance factor has been included in the return period itself. So if we want to compare the previous code with the new code, we have to look into this definition of maximum considered earthquake. So AC7 2016, it defines this maximum considered earthquake as 84 percentile earthquake, 84 percentile estimate of response spectrum obtained using DSH. So if we are performing deterministic seismic hazard assessment, we can get MC as 84 percentile, or 84 percentile of deterministic seismic hazard assessment is close to the MC. So in reality, the concept of MC is not there, or DB is not there in deterministic seismic hazard assessment, because it comes along with the return period. And return periods or probability of accidents we are not getting in DSHA, that is coming in PSHA only. So it was defined for equivalence. So if we want to develop an equivalence between DSHA and PSHA, then for equivalence it has been observed that 84 percentile of DSHA is close to MCE obtained from PSHA. If we go back earlier code, AC7 2005, it was defining that 150% of the median, that is 1.5 times of median obtained from DSHA, was equivalent to MC. So this also shows that this 1.5%, 1.5 times of median is close to 84 percentile, and that is close to MC. So MC 84 percentile and 1.5 times the largest median, these are same. So with this background, we can correlate our previous code with the terminology of DB and MC. The IS 1893 Part 1 2016 does not define what is DB and MC, but we can correlate it with this understanding that 1.5 times of median obtained from deterministic analysis corresponds to MC. So the zone factor Z, which was given in our earlier code, was median effective peak ground acceleration, which we also call zero period acceleration, obtained from DSHA. And 1.5 times Z will give us the MC. And half of that, 50% of MC, that is considered to be DV. So DV is considered to be half. This relationship still holds good. I will show later that current code also have similar relationships. And when we consider Z by 2, that corresponds to serviceability earthquake. Serviceability earthquake is required in case of working stress design or serviceability level checks, if any, we have to perform. Currently, our code has removed all serviceability level concept in case of earthquake. So earthquake is considered to be a strength level design action, not serviceability level action. But for the parity with the working stress design, because for some of the structures, working stress method is still used. So for that, we need a definition of the serviceability earthquake as well. And the response spectrum, which is given in the code, that is the shape of the response spectrum. And in this response spectrum, this value, which corresponds to zero period, this is important. This value is what we call effective peak ground acceleration, EPGA, or zero period acceleration, and the zone factor. Now, our code gives this value as 1, which tells us that actually it is a normalized shape. It is not the response spectrum, but it is the shape of the response spectrum, which is giving the relative frequency content only. So it has information about frequency content. It does not have information about amplitude. So this nomenclature, by calling it SA by G, is also actually not theoretically correct. It should have been SA by Z. And then this value will become 1. So each response spectrum, if we divide by corresponding Z value, then this will be Z. So this is a normalized shape. And this we can call SA by Z. And if we multiply it by 1.5 Z, then it becomes response spectrum corresponding to MC. And if we multiply it by 1.5 Z by 2, that is 0.75 Z, then it becomes DVE. And if we multiply it by Z by 2, then it corresponds to serviceability earthquake. So the relationship between MC and DVE is 1 by 2. Between DVE and SE is 1.5. Now, in the current code, okay, similar thing is there in case of ASC 7. So in ASC 7, DV is used to define the response spectrum. In our code, the zone factor Z is used to define the response spectrum, and Z by 2 is actually serviceability level earthquake. This we have to understand. Z by 2 is not DVE. This is the common confusion that most of our designers, they think that the code is using Z by 2 into I by R into SA by G. So Z by 2 is corresponding to DVE. Z by 2 is not corresponding to DVE. Z by 2 is corresponding to serviceability earthquake. And to make it DVE, we have to multiply it by 1.5. And that 1.5 was given in the load combination. So for working stress method, we have to use serviceability level earthquake, which is corresponding to Z by 2. And for DVE, we need the earthquake corresponding to 1.5 Z by 2, which we will be using, or which we can use in limit state design. So this we have to keep in mind. Similar relationship, or rather reverse relationship, is there in ASC 7. In ASC 7, for limit state method, the load factor is 1 for earthquake. And for working stress method or allowable stress design, the load factor is 0.7. So they define the earthquake force corresponding to DVE and then reduce it by a factor of 1.5 to convert it into serviceability earthquake for working stress design. In our case, we define serviceability earthquake in terms of Z by 2, and then multiply it by 1.5 to get the DV level earthquake, which we can use in limit state design. So this inverse relationship we have to be clear, then we will be able to compare the current code and the new revised code properly. So this is the zonation given in revised code in 2025. The revised code has now 5 zones. The earlier code was having 4 zones. It is having 5 zones starting from 2 and going up to zone 6. So zone 1 is not here. Even in the revised code, we can see it is starting from zone 2, just to have a parity with the history of this zonation development. Because initially in 1960, when the code came, there were zone 0 and zone 1 also. Later on in successive revisions, zone 0 and zone 1 were merged into zone 2, and zonation was changed. And then we have zone 2 to zone 6, just to emphasize that none or no place in the country is free from earthquakes. Minimum we are having zone 2. Now, if we look at the factors, I will come back to these factors later. The code defines 4 types of structures now: the normal structures, important structures, critical structures, and special structures. Definitions of these are given, although those definitions are not entirely clear. I can understand some difficulty may be there, but we can relate this definition with respect to importance factor. Earlier, we were using 3 importance factor or 3 importance classes of the buildings: importance factor 1, importance factor 1.2, and importance factor 1.5. So these are now considered in the code as normal structures, important structures, and critical structures. But one more class has been introduced as special structures, and this is having an importance factor of 2.0. So you can think like it is a class which corresponds to an importance factor of 2.0. It is more important than the hospital buildings, which we were designing previously for importance factor of 1.5. Now the code defines these classes and also the corresponding return period for which these needs to be designed. So special structures needs to be designed for a return period of 4,975 years. The critical structures needs to be defined for a return period of 2,475 years. Important structures for 975 years, and normal structures for 475 years, consistent with the definition of DV, design basis earthquake. Our code does not define the DV and MC in the sense it is defined in other codes. Rather, it defines a design earthquake with different return periods. Now, these different return periods incorporate importance factor and the load factor in itself. So if we take that into account and then try to compare our code, we will be able to compare. Similarly, in case of working stress method, which earlier we were designing for submissibility earthquake, for that also different return periods are given. For normal structures, it is 175 years. For important structures, 275, critical 475, and special 975 years. Now, the code provides zone factors with these different return periods. Here it is important, this 475, this is our DVE. Conventionally, what we have been calling DVE, or corresponding to importance factor equal to 1. This 975 years, this is corresponding to an importance factor of 1.2. And this 2475 years, this is corresponding to an importance factor of 1.5. And we can see that the ratio tells us the importance factor. So I told that importance factor is included. So in case of higher zones, let us say zone 6 and zone 5, this ratio is 1.2. Now here it is important that the ratio in the zone factor to be used for important and critical structures and the normal structures is not same in all the zones. Earlier, the importance factor was same across all the zones. So when I was designing hospitals, the importance factor of 1.5 was to be used throughout. But here we can see that actually this importance factor is changing. The ratio between the JAD for 2475 and 475 is changing. In case of lower seismic zones, zone 2 and 3, this is 2. So 0.075 to 0.15, 0.125 to 0.25. So we can compare it here in zone 4, 5, and 6. These importance factor are 1, 1.2, 1.5, and 2. In zone 2 and 3, the ratio is different because the seismicity is different. So it is 1, 1.33, 2, and 3. Now you can also see the relationship between dB and MC. So this relationship is also changed. So dB corresponding to 475 years, MC corresponding to 2475 years. In case of lower seismic zones, this ratio is 2. So earlier we were using 1.5 JAD by 2 as the dB and 1.5 JAD as MC. So ratio between MC and dB was 2. In case of lower seismic zones, it is still 2. But in case of higher seismic zones, this ratio is 1.5, which is consistent with ASC 7. Because in ASC 7, to convert MC into dB, we are using a factor of 2 by 3, that is 1 over 1.5. So there the factor from dB to MC is 1.5. So in case of higher seismic zone, we are also having the same factor, 1.5. But in lower seismic zones, we are having that factor as 2. So this is because the shape of the hazard curve in northern India and southern India, peninsular India, is different. Due to that, because the slope is different, due to that, the value of zone factor, which is nothing but EPGA, effective peak ground acceleration, that is different in different zones. And this ratio, it is already well known. It was already well known that it varies between 1.5 to 2. Our code was earlier having 2, and American code was having that ratio 1.5. European code was also having that ratio 1.5. Now this PSHA, which has been performed in our revised code, that also confirms that this ratio within our country also varies from 1.5 to 2. Then the other issue which has been introduced in this code is site classification. Site classification was earlier also there. Earlier there was site class or site type, solid type 1, soil type 2, soil type 3. Now the classification has been changed to A, B, C, D, and E. And it is very similar to what is given in ASC 7. So ASC 7 defines these 5 classes A, B, C, D, E, depending upon the shear wave velocity. So in feet per second, in meter, it can be converted roughly to 1/3. Now in ASC 7, in terms of into 2022, similar classification is given. Europe code also has similar classification. So our code, IS 1893-2025, that also defines the shear wave velocity range, and based upon that, the site classes are defined. So above 760 meter per second, that is considered to be rock. So A is like hard rock, B is soft rock. So rock starts from 760 and it goes beyond 1500. So site class A and B is considered from American code. Now the definition of A and B in Eurocode was different. In Eurocode, there is only one type of rock, so which starts from 800 meter per second, close to 760 meter per second. So we can see that this definition is similar, but the site class A is actually site class B of our code and American code. Then site class C, which is stiff soil, and site class D, which is medium to soft soil, and site class E, which is very soft soil with shear wave velocity, average shear wave velocity less than 180. Now here, one important issue is that generally other codes, American code or European code, when they are considering the shear wave velocity, they are considering the shear wave velocity in top 30 meter, and they call it VS30. So our code is not using VS30. Our code is using average shear wave velocity in the depth of influence of any structure. So that is also defined in the code for different types of foundation, what will be the depth? For example, in case of spread footing, the depth will be 2b, where b is the plan dimension. In case of mat foundation also, it will be 2b. So if you are providing a mat foundation or raft foundation, or you are providing a spread foundation, the depth of influence will be different. And accordingly, the average shear wave velocity will also be different. This appears a bit awkward to me, that site class will depend upon the structure type or foundation type. In case of piles, it is still deeper. So depending on what type of foundation and structure you are providing, it will result in different classes. So that's how it has been considered in our code. As per my understanding, the depth of influence is important for bearing capacity. The concept of the pressure valve and depth of influence, that we have studied in our graduations, and we know that the soil within that influence zone, that is affecting the bearing capacity. But to me, same does not appear true for the earthquake motion, because in case of earthquake motion, we obtain free field ground motions, and free field ground motions are affected by the top layers of the soil mold. Although there is a debate whether 30 meter is adequate or not, and there is a lot of evidence that the 30 meter may not be adequate, but at a site, variation from structure to structure, the site class will vary. The same site, the class will vary from structure to structure. That appears a bit awkward to me. I'm not able to convince myself to that, but that's what is given in the code. And maybe some debate will be there in future and may or may not change. But currently that is the situation. And this will be obtained like this. So average shear wave velocity, this is nothing but weighted average of shear wave velocity of each layer. And weight of in that weighted average is the depth or thickness of that particular soil. So HI is thickness of that soil layer, and then we can get the weighted average. Shear wave velocity can be obtained directly by measuring in site, either using geophysical methods or cross borehole. Now, in many cases, if the shear wave velocity is not measured directly, the code also provides the conversion formula from SPT test. So if we have the n values from SPT test, using these formulae, we can convert that into shear wave velocity, and we can get average shear wave velocity in the influence zone, or the depth of influence of the structure. And that average velocity will decide the site class. So we have to read the site class from here, and the site class will define the shape of the response spectrum. So the shape of the response spectrum, which I have shown earlier, in terms of mathematical equations, it is written like this. So between 0 to 0.01 second, very rigid case, I said, it is 1. It is increasing linearly from 0.01 to 0.1 second. It remains constant from 0.1 to 0.4 second in case of site class A and B rock, up to 0.6 second in site class C, and up to 0.8 second in site class D. Most of our structures are in this velocity controlled range. This is important. So this is 1 by T in case of rock, 1.5 by T in case of site class C, and 2 by T in case of site class D. So if you compare this with soil type 1, soil type 2, and soil type 3 of our previous code, you can see that there is an upgradation. For site class soil type 2, earlier it was 1.36 by T, which is now 1.5 by T. In case of site class 3, it was 1.67 by T. Now it is 2 by T. So this factor has increased. So effect of soil amplification in velocity controlled range and displacement controlled range has been increased. But that effect in the accretion controlled range is not considered, and it is understood. I have listened to some presentations, and it has been explained there that this short period amplification is considered within the Z value itself. And it is also mentioned in code that in case of those zones where we are having metamorphic or igneous rocks, this factor is 1. In case of sedimentary rock, this factor is 1.5. Laterite layers, it is 1.35, and in case of alluvium, it is 1.5. So if we are considering alluvium sites, then the Z value is already incorporating a factor of 1.5. And then if we compare it with this amplification factor, so 1.5 from there and 2 from here, so total amplification becomes 3, which appears to be much larger. So if I compare it with ESC7, in acceleration controlled range and velocity controlled range, these are the soil factors. So we can see that in acceleration controlled range for site class up to site class D, the maximum value is 1.6. Whereas in our code, this is 1.5. So that appears to be close. But when we go to FV, then the maximum value is 2.4, whereas in our code, that appears to be 3. Site class E is different. Our code asked for a different treatment of this. AC7 also considers different treatment, but this soft soil, soft alluvium, this maximum factor is 2.4. And it also depends upon the amplitude of the motion, because as the amplitude of the motion increases, non-linearity in the soil increases, and there is reduction in amplification because energy dissipation takes place. So it goes up to 1.7. So actually it is varying from 1.7 to 2.4. Our code is taking it 3. So this appears to be on higher side to me, and which needs some discussion and debate in the future time, and perhaps it will be corrected or adjusted. Currently, to me, it appears slightly on higher side. You may think yourself, and we will have a discussion on this. Now, vertical ground motion. So earlier, the vertical response spectrum was considered as 2/3 of the horizontal response spectrum. In the revised code, the convergent factor is not constant. Convergent factor also depends on the period. So in the period range up to 0.01 second, this is 0.82, and for period greater than 0.1 second, it is 0.67. But in the range in between 0.01 to 1 second, it is varying from 0.82 to 0.67. But as I said, that most of our structures will have period greater than 0.1 second. So these first two are not yes, here we are talking about vertical period. So in vertical direction, any structure is very rigid. So in vertical direction, it is possible to have periods less than 0.1 second. And then it is possible that we may have to use this middle row also. So this may be valid for our cases, at least some of our structures. But for structures having longer period in vertical direction, 0.1 second, then this value is 0.67, same as it was there in the previous code. Then the reduction in the ground motion amplitude with depth, that is also considered. It was there earlier also. At 30 meters, we were considering 50%. Same is continued in this code. Only thing is that here it is considered for, it is rather given explicitly for vertical component also. For horizontal component, it was already there. In case of vertical component, same reduction is provided for vertical component also in the revised code explicitly. So in case of below ground motion, or the components of the structures which are below ground surface, those structures which are buried inside the soil surface, we can reduce the inertia force. So the code says that this inertia force, the estimated inertia force, can be reduced, but the above ground forces or the portion of the structure above ground, that will be subjected to normal forces which will be obtained from the full response spectrum. Or the estimation of the inertia forces below the ground surface, only only that portion will be subjected to reduction. That is one. And a portion of the soil which is surrounding the structure or which is acting as backfill, that will also be considered in case of granular material. If it is granular material, then only it will be considered. If it is clayey material, then we can understand that the gap can be created, and then it is not necessary to consider that. Now, the effect of damping is also explicitly mentioned, and it is interesting. Earlier, the effect of damping was uniform over the whole period range. Now, the effect of damping is also different in different period range. Between 0.01 to 1 second, we will use this. It is constant between 0.1 second to TAV. So TAV, as I explained earlier, this is representing the velocity controlled range, acceleration controlled range. So in acceleration controlled range, this will be constant. In displacement controlled range, beyond 6 seconds, there will be no reduction because of the damping. And in the velocity controlled range, it will be linearly varying. So from eta max, it will be linearly varying, and similar relationship is also given for in vertical direction. So in vertical direction also, same effect of damping will be considered. So the damping will be, the effect of damping or reduction due to damping will be constant in acceleration controlled range. It will be, there will be no reduction in displacement controlled range, and in velocity controlled range, it will vary linearly from the maximum reduction to no reduction. So this is a new provision in the revised code, which we have to be clear about. And this value of eta max, that is also given depending upon the value of damping. If the damping is more than 5%, then this last expression, tan over 5 plus 100 times xi to the power 0.5. So this we will use here. Xi is given in terms of fraction, not in terms of percentage. So when xi we give in terms of fraction, we will use this. If xi is between 0.5% to 5%, then this expression. If it is less than 0.5%, then we will use this expression. So these expressions for different damping ranges are also provided. Now going to the next step, once the response spectrum acceleration is identified, how to calculate the forces. So same philosophy, as I said, is being used. In case of horizontal force, it will be reduced by response reduction factor R. Earlier, there was an error actually. In case of vertical direction, also this response reduction factor R was given, but that was an error because in vertical direction, energy dissipation cannot take place. Inelastic energy dissipation cannot take place because if the hinges are formed in columns in the axial action, okay, that will be a brittle field. So under axial action, the hinge formation is not allowed. It is under bending, and that is occurring because of the lateral action of the force. So there is no response reduction factor in case of vertical direction, or the response reduction factor for vertical component of earthquake is going to be 1. And in later calculation, perhaps Dr. Vijay will show you, this will make a lot of difference because the vertical component of earthquake, which we were calculating earlier by using a response reduction factor of R, although that was wrong, but our code was giving it like that, that is going to increase by R times. So vertical component will become very, very significant now with this correction in the code. So there is no inelastic energy dissipation in vertical direction, and hence no R is appearing in this formula, or in other words, we can say that R is equal to 1. The code also defines minimum design force. So if we calculate the design force using the response spectrum and response reduction factors given in the code, it should not be less than this value, 0.625 Z I by RW. So it cannot be less than this. So a minimum force is defined, and it should not be less than, in no case it can be less than 1.5% of W. So H in our previous terminology, minimum value can be 1.5 W, and it also depends upon the zone. Similarly, the design displacements are also defined. So design displacements in different zones, that is 0.4%, same as in our existing code. So there is no change. Then in case of architecture and non-structural components, also the procedure to calculate earthquake force is given, and that can be obtained using this expression. So actually, when any building is vibrating, the acceleration at the top floors is higher than at the ground level. At the top, it is roughly 2 times. In some cases, people have reported higher than 2 also, but on an average, 2 times. And the variation is following the shape of or the mode shape of the fundamental mode. In code, it has been considered linearly. So we can see that this Z, which is nothing but peak ground acceleration or acceleration occurring at the ground floor, that is multiplied by this factor 1 plus x by h. And when this x becomes equal to h, that means at the roof, this factor will become 2. So 2 times this will be considered. So at roof, and it is varying linearly. So this is the equation of a line. So it is considered linearly varying from EPGA to 2 times EPGA. And then it is multiplied by the importance factor, a factor A. This is response reduction factor of the non-structural components and the weight of the non-structural components. And it should be at least 4% of the weight of the non-structural components. So this has also been included in the revised code, and the factors small a and r for different types of non-structural components are provided. So this a and r for different components, non-structural components, including partition walls, cantilever elements, the chimneys, stacks, these are provided in the code for all possible structural, non-structural components. Now this site class E, which we discussed, this is a special case when we are having the soil very, very flexible, or it is prone to liquefaction. Now in such cases, what is to be done? The code provides the methodology. So first we have to try to improve the site class, and we have to improve it so that it comes to a level of site class D. So then we can use it for similar to site class D. So the improvement will be tried. So if improvement up to site class D is not possible, then we have to do special analysis, site-specific response or ground response analysis. And using that ground response analysis, we can calculate the seismic hazard or the Z value at the surface of such soil sites. So a special analysis is required for this. Then the code also talks about response spectrum versus time history analysis. This is an important feature of the revised code. The code emphasizes on use of time history analysis, and this question all of us face, that whether it is necessary to go for time history analysis, or which are the cases in which time history analysis is required. Is response spectrum analysis accurate enough or not? So response spectrum method, where mostly we are using mode superposition. So mode superposition is valid for linear structures. So in case of linear structures, response spectrum analysis is almost as accurate as the time history analysis, provided we are able to consider modes up to 90% mass participation. The problem occurs when we are not able to consider, or we are not able to get the modes up to 90% mass participation. In that case, we do some missing mass correction, but still the results are inaccurate. So in those cases, time history analysis becomes necessary to get the accurate response of the structure. And in case of nonlinear structures, although currently our code is not talking about nonlinear analysis, but in nonlinear, when the structure is either yielding, it is going into inelastic range, or it is having some device which is having nonlinear behavior like a damper or a base isolator. So in that case, time history analysis becomes mandatory. We have to go for time history analysis. In case of irregular buildings also, the code suggests that we should go for time history analysis if we want to do soil structure interaction, the complete soil structure interaction, not only the flexibility of the soil, but we want to consider the effect of wave propagation in the soil. Then also time history analysis becomes mandatory. And in case of response spectrum method, we are using 100:30 combination rule, whereas in time history analysis, we can consider two orthogonal components simultaneously. So this 100:30 rule is not required. Now, how many minimum ground motions we should take? As I said in the beginning, that each ground motion is signature of a particular earthquake, and the ground motion which is going to actually affect my structure has not been recorded so far. That is going to be unique. So therefore, I can't use any one ground motion. Multiple ground motions are needed, and minimum 3 ground motions are recommended for linear time history analysis, and 11 ground motions are needed for nonlinear time history analysis. In case of, as I said, in case of special seismic devices where we are having nonlinear behavior like base isolation device or damping device, we have to go for nonlinear time history analysis or equivalent linear time history analysis. Now, with all this, even with our revised code, with such complicated design methodology, what we are going to achieve, this is still unclear in our codes. So what we are expecting. So 2002 code in its foreword, it was saying that as far as possible, the structure will withstand moderate earthquakes without structural damage and heavy intensity earthquakes without total collapse. So that was the expectation, but we can see here it is quite qualitative. It is not quantitative. We can't exactly tell the owner that what damage the structure is going to sustain or what performance is expected if the structure is designed as per code. And even for ensuring no collapse, there was no provision in the code, and accordingly in 2016 code, this was revised, and it was said that structures designed as per this standard are expected to sustain damage. That's it. But how much damage? That was not mentioned. So we do not know whether the structure will damage to an extent that it is going to collapse, or it is going to damage only slightly. That information was not there. The code was not having any framework, any methodology to identify that. Now in 2025, code defines this in terms of serviceability, in terms of structural elements and in terms of non-structural elements, but still this is vague. So slightly more quantitative or in an improved direction we have gone, and the code says that buildings or structures designed with these standards are expected to sustain damage when subjected to design ground shaking specified in this standard, but not collapse. So it has included no collapse again if it is designed for the earthquakes, but if it is subjected to earthquakes higher than that, then no collapse is not guaranteed. So for example, if a normal structure which is designed for 475 earthquakes, if it is subjected to MCE, then no collapse is not guaranteed. No collapse is guaranteed by this code only if the structure is designed for the same level of earthquake. So for example, a hospital building designed for 2475 years, that can sustain MC level earthquake without collapse, but it will be subjected to damage. More than that, that information is not available in the code, even in the revised code. In case of non-structural components, architecture and other units, the structure, the code only says that these non-structural components are expected to perform better than those merely provided without these observations. So it only says that the performance will be improved. But what will be the level of improvement? Whether we will be able to achieve a targeted performance or not, that our code is still silent. So that is still not achieved. And if we want to do that, we have to go for performance-based design. And regarding soil structure interaction, the code has included soil structure interaction only in a limited way. So only two effects are included, and those two effects are one is the soil flexibility, and another is inertia force of the mass of the soil foundation system. So foundation and a small soil portion surrounding the foundation, whatever is the inertia force of that, that is included, but it is not complete soil structure interaction. Complete soil structure interaction has another important component, that is the wave propagation within the soil and interaction of the structure with that wave propagation. That part is still not there in the code, and hopefully in the future revisions that will come. So thank you very much. These were the salient features, salient changes which I wanted to discuss. I hope you have written your questions. We will take up the questions towards the end of both the sessions, but we are having some 15 minutes break at the moment.
Yeah.
And then we will meet again after 15 minutes. And then I will take up the changes in part 5. Thank you.
Okay.
Thank you, sir. Thank you for the wonderful session. The question answer session for this presentation we will be taking after the second session. Now we will be having 15 minutes break. We will join the session at near 3:55. I hope everything is okay with that.
Okay. So we will meet at 3:50.
Okay. Yeah. Thank you, sir. Hello. Welcome back, everyone. We are about to start our next session of Dr. Yogendra Singh. Jen, sir? Okay. Over to you, sir. Yogendra, sir. Am I audible to you?
Yes. Thank you. Thank you.
Yeah. Thank you,
So,
sir.
I hope my screen is visible.
Yes, sir, it is visible, but make it on presentation form. I can see your whole
Yeah.
PPT slides. Yeah.
I don't know why. Okay.
Yes, sir, it is visible now. Yes, sir, it is now.
Okay, so welcome back. Now we will take up the salient changes in part 5, which is related to buildings. And in, as I said, IS 1893 has these 11 parts. And out of these 11, 2 parts have been published so far. Part 1, general provisions, which we discussed so far. And part 5 is related to buildings. And in part 5 itself, there are 4 sections. And these 4 sections, section 1 gives additional criteria in addition to what is given in IS 1893 part 1 for all structures. So regarding buildings, building specific provisions, those are covered in section 1. Then section 2 is dedicated to masonry buildings, what special provisions are required for masonry buildings. Section 3 is related to concrete buildings or RCC buildings, and section 4 is for steel buildings, additional provisions. So I will be focusing on section 3, which is additional criteria for concrete buildings. And of course, whatever additional criteria are given for all buildings, those are also applicable. Now the code says that except Adobe buildings have been still kept in IS 13827 and 13828. All previous provisions of IS 1893 part 1 have been included in these sections. So this will override IS 4326 and other provisions wherever those were applicable. So the changes which have been summarized in the foreword of part 5, the major changes. The first change is regarding response reduction factor. It has been renamed. Values are more or less same as what they are in the earlier code, but its name has been changed to elastic force reduction factor. In place of response reduction factor, it is now more appropriate to say elastic force reduction factor, because our design philosophy is such that first we calculate elastic force, the force which will be acting on the elastic structure. And because our structure is designed to go into an elastic range, we reduce the forces by a factor depending on the energy dissipation capacity of the structure, and that is factor R. So that it has been renamed now as elastic force reduction factor. And the code says that some more structural systems have been included, and response reduction factors for those structural systems have been provided, and some values have been revised. We will discuss those values in more detail. So importance factor have been adjusted in view of the revision of the hazard level. As I said, that importance factor has been included in the return period itself. So there is no additional importance factor required. So that's why for RCC buildings, all buildings, that importance factor is actually 1. So it has been retained in the code just for any future need. but actually the importance factor is not there. All values are 1. And provisions on design for torsion in case of buildings about vertical axis, torsion about vertical axis have been improved. So earlier there was only change of torsional flexibility and eccentricity. Now a more comprehensive way of considering both of these together have been included. And these provisions on buildings have been harmonized with relevant provisions of IS 4326, and additional provisions for earthquake resistant design of critical buildings have been included. And serviceability check under the effects of earthquake loads are dispensed with. As I said, that there is nothing like serviceability check under earthquake. Earthquake action is a phenomena which governs the ultimate state. So serviceability level check has been dispensed with. Only historically it is there in some codes, not this code, but in some other codes it is considered, or serviceability level earthquake is required for using working stress method. But as such, any serviceability level check, and this clarification is important with respect to the previous confusion in the code. There was an error in the code where the interstory drift was checked for serviceability level earthquake, not for the strength level earthquake. So that confusion is cleared here. Nothing is to be checked for serviceability level earthquake. So interstory drift will also be checked for the design level earthquake, and design level earthquake will correspond to different return periods as discussed earlier. Then additional criteria for concrete buildings, the changes which are included in section 3. There is a new expression for fundamental natural period. So previous expressions have been revised. Now a very comprehensive expression which takes into account the columns, shear walls, as well as masonry infills has been provided in the code. Then admissibility of different structural systems in different earthquake zones is provided. So earlier there was no restriction on using any particular structural system in a particular zone. Now, similar to IS 16700, where in case of tall buildings, different structural systems were provided in, or there were restrictions on use of structural systems in different zones. Similar provisions for non-tall buildings or short buildings having height less than 50 meters have also been provided. And the variation of structural plant density is also provided. So rather than controlling only the area in plan of the walls, now the code controls the total structural plant density, that is the area of columns, walls, everything. Then it has been clarified that this code is not applicable to these two types of systems which consist of only walls and slabs. So there are no beams, but there are only walls and slabs, and there are no columns. So such structural systems are not covered by this code. And structural walls, slabs, and beams with beams oriented perpendicular to minor axis of the thin structural walls without boundary elements. So the beams which are connecting to the shear walls in autoplane direction, and there is no boundary element provided there, so that the joint cannot be detailed properly. Such buildings are also not covered. What is meant by not covered, that is not clear. Whether such buildings can be designed using some other code or not, it's not clear. But my interpretation is that it means that such buildings are not allowed to be constructed as per this code. So this code prohibits use of such buildings, because these buildings, their performance during earthquake is doubtful. Then a new structural system, core, structural wall, perimeter column, outrigger, and belt truss system this has been introduced, although the definition is not very clear, and advantage of this structural system is also not very clear in seismic region. So basically this is core and outrigger system where a shear wall core is provided, the columns are provided on the perimeter, and to take the advantage of columns, those are connected to the core through outrigger, and together those perimeter columns are connected through bend. So this type of system is prescribed, although in my opinion ductility of such systems is doubtful. I don't know whether there is any background study for this or not, where it has been shown that these structures are having adequate ductility, but otherwise in my opinion such structures are not very desirable. But this has been included in the code. Actual basis of including these structures in the code will come when we will be having commentary over the code, and then we will know what is the background and is there any supporting literature for this or not. Then gravity columns have been, although gravity columns were existing in previous code also, here some more clarity has been provided about gravity columns, and it has been mentioned, as it was there earlier also, that gravity columns will be designed for gravity loads, and these will be designed for forces due to displacement compatibility induced by the roof and floor slabs during earthquakes. In other words, that these will be designed for R equal to 1. Displacement compatibility means that these will be designed for the full displacement or the displacement corresponding to R is equal to 1, and whatever forces are developing with R equal to 1, these will be designed for that. So such systems have to be quite flexible, because currently the trend in our industry is that if there is any component which is creating any problem in design, which we are not able to design, we declare it as gravity column or gravity member, and we simply ignore its response during earthquake. That's not correct. The code is making it clear that displacement compatibility is to be satisfied. More details of this will be available when IS 13920 is also published. So IS 13920 will also have similar parts, part 1 to 11, corresponding to different buildings or different types of structures. Then in clause 7 of the criteria for earthquake resistant design of all buildings, the code specifies the desirable attributes of earthquake resistant buildings. So these were there earlier also, but code has put it in more clear language. The first one is robust structural configuration. So structural configuration earlier was given in terms of irregular. So those types of irregularity are still there. Some of the irregularities have been modified, more details are available, but that still forms the part of the code. And at least a minimum elastic lateral stiffness that is controlled by interstory drift in case of buildings, and at least a minimum overall strength, lateral strength, the minimum base shear, and adequate ductility. Adequate ductility will come from the ductile detailing code. So once the ductile detailing code is also published, which is going to be very similar to the existing 13920. So once that is there, that will, until that date, the existing 13920 will govern the ductile detailing. So that is to be followed. Now, the code tries to define the irregular modes of vibration. Earlier also there was a lot of confusion. The code has tried to redefine that, but still the confusion is not very clear. At least to me, it is not very clear that what the code is trying to say. So code says that if any one of the two conditions is satisfied, or any of the two conditions are there, then the building will be said to have irregular modes. And these two conditions are that first three lateral translational modes do not have 65% mass participation in each direction, or the building has closely spaced modes. Closely spaced mode definition is same as in the existing code. That means the difference between the two periods is less than 10%. So then it will be said as closely spaced modes. And any of the two conditions. So please note this or in between. So it is or, not and. So earlier there was confusion that whether this is and or, whether both the conditions are required to call the building irregular, or any one condition will render the building irregular. So it clarifies that any one of the two conditions can cause the building to be classified as irregular. And if the building with irregular modes, I mean this later portion which the code clause clarifies, that is not clear to me. What it is trying to say, that in zone 2 and 3, it shall be ensured that first three lateral translational modes of the building together account for at least 65% in each principal direction. So it is unclear what the code is trying to say. What I'm understanding for this is that in zone 2 and 3, the second condition is not important. The first condition needs to be satisfied. So if first condition is satisfied, then the building will be said regular. In zone 4, 5, and 6, these three conditions needs to be satisfied. So first three lateral translational modes should have 65% seismic mass. The fundamental lateral translational natural period should be spaced with a difference of more than 10%, and the first mode should not be torsional mode. So the period of the lateral translational mode should be longer than the torsional mode. So torsional mode should be rigid. In other words, it is controlling the torsional rigidity of the building and separation of the modes, or all the three conditions are to be satisfied in buildings with zone 4, 5, and 6. So in zone 4, 5, 6, any of the three conditions, if it is not met, the building will be declared irregular. Whereas in zone 2 and 3, only this condition is satisfied, or only the first condition is adequate to define the building to be regular. That means closely spaced modes is not a problem. And torsional flexibility also does not appear to be a problem as per the language of this code or this clause. Then the stiffness modifiers have been defined in case of different buildings. I'm focusing here only on the concrete buildings. So in case of RC slabs, in outer plane it is 0.25, in plane it is 1. To me, this 1 in plane appears to be on higher side. So if you go into IS 16700, there this maximum stiffness factor is 0.5. Here it is defined as 1. Similarly for beams, it is 0.35 about major axis and 1 about minor axis. Usually bending about minor axis does not take place because our beams are monolithic with the slab. So this minor axis does not come into picture. So 0.35, which we take about major axis, it remains same as it was in the earlier code. And in case of columns, it is given 0.7. So it's also same as in the previous code. Then structural walls, in plane and outer plane, both stiffness modifiers are defined as 0.7. So 0.7 for in plane to me appears to be okay, but 0.7 in outer plane appears to be higher, because in outer plane the cracking in the shear wall is more, and the other codes like AC7, they define a lower stiffness modifier. Then other components like transfer girders, joints, those remain uncracked. So their stiffness modifier is 1. Similarly, the response reduction factor or elastic force reduction factor as defined in the new code, that has the same values. Earlier we were expecting that there may be some changes. Some of the response reduction factors may be increased, but please note that there is no increase in the response reduction factor. For all the structural systems, these remain same. In case of flat slabs, also it is same, and two types of flat slabs. Flat slab type 1 and type 2 are defined, FS2 and FS1. So FS1 is the one which is not having any intermediate columns. We have the core and the perimeter columns only, whereas in FS2 the intermediate gravity columns are also there in addition to the perimeter columns. So two types of flat slab systems in combination with SMRF and special shear walls are defined, and the response reduction factor for all these buildings is defined as 3. Then the methodology for design of buildings with basement has been clarified, and it has been allowed to consider the buildings with basement in two parts: the portion A, which is above the ground level, and portion B, which is below the ground level. So for portion A above the ground level, the forces shall be estimated as usual, or in other words, by assuming it to be supported at the top of the basement or top of the podium, the tower will be designed similar to a structure which is resting on directly on the ground. So that will be the period formula will also be same. The method of calculating AHD will also be same. AHD and AVD will be same, and the distribution will also be the same. So portion A will be designed in the same manner as any building resting on the ground. The portion B, which is below the ground, there the earthquake force in horizontal and vertical direction will be calculated separately for its own inertia force, and here the value of SAYG will be considered in the peak range. So please note that here it is considered 2.5 for horizontal as well as vertical. The only difference between the design acceleration coefficient for horizontal and vertical direction is that in horizontal direction we divide it by R, and in vertical direction we do not divide it by R. So it is assumed that this structure, portion of the structure which is inside the soil will be quite rigid, and it will be in the acceleration controlled range, where the normalized shape provides us a coefficient of 2.5. So this SAYG value will be used as 2.5. Okay. Now, once these forces are calculated, base shear is calculated corresponding to these expressions, these will be distributed, and the distribution will be same as in other buildings. So whether it is portion A or portion B, although it is given separately, but actually it leads to the same. So in the same manner, that is horizontal force will be distributed in proportion to h square, and the vertical force will be distributed in proportional to h. Now the formula for period of vibration has been revised. If you compare it with the earlier expression, that is 0.075 h to the power 0.75, now it is this 0.075 h to the power 0.75 in the numerator, and in denominator we have several parameters now. This rho cc is the planned density of concrete columns. So this is giving the column density. So total cross-sectional area of the columns divided by the plan area. So that will give us rho cc. Then rho CSW. So this is shear wall. So for shear wall, planned density is rho CW. LCWI is the length of the ith shear wall, and h is the height. So length to height ratio, that will also come. And rho MW is the masonry wall, the partitions. So if density of partitions is also taken into account. So this formula takes into account the column, the shear wall, and the masonry infills together. And it is applicable to all buildings, whether those are having shear walls or not, whether those are having masonry infills or not. So the single formula will now cater to all types of buildings for calculation of period, all types of RCC building for calculation of the period. How does it compare with the existing formula? That need to be seen for different types of buildings. When it will be compared, then we will know the true implication of this formula, that how much change in the period is occurring because of this. And for buildings with height less than 50 meters, because this code now very clearly qualifies the provisions height less than 50 meters. So it is now separating the scope of IS 1893 and IS 16700. So IS 16700 is applicable for buildings with height less than, more than 50 meters, and IS 1893 is applicable to buildings less than 50 meters. And it says that the design horizontal earthquake force, the minimum value, this I discussed in the previous part, and this 0.625 Z by R into W, and minimum it is to be 1.5% of W. So the minimum base shear is given. The distribution of the horizontal base shear is proportional to H square, because the horizontal mode shape is considered to be parabolic. So we know that the distribution of the force is or has to be proportional to the fundamental mode in that direction. So the fundamental mode in horizontal direction is considered to be parabolic, whereas the fundamental mode in the vertical direction is considered to be linear. So please pay attention to this difference. Here it is, in vertical direction it is considered to be constant. So it is assumed that the building will move vertical. So in case of horizontal direction, it is proportional to HI square, WI and HI square, whereas in vertical direction it is proportional to WI only. So it is proportional to only the weight. So it is assumed that the whole of the building will move rigid as a rigid body, and the acceleration, vertical acceleration along the height will remain same. Then regarding the combined effect of torsional eccentricity and torsional flexibility. So when we talk about torsional irregularity, two parameters or two parts are important. One is torsional flexibility and another is torsional eccentricity. So torsional eccentricity is because of the separation between center of mass and center of stiffness. So if center of mass is away from center of stiffness, the earthquake force will act at an eccentricity with respect to the center of resistance, and due to that torsion will be caused. So this is this is indicating the amount of torsion which is getting generated in the building. On the other hand, torsional flexibility reflects the dynamic behavior. So if a building is torsionally flexible, amplification of torsion will be more. So both torsionally flexible and the buildings have too much eccentricity, both are to be avoided. So this single factor takes into account both, and it includes three ratios. One is this EK I by B. So this EK is nothing but the eccentricity between the center of mass and center of stiffness, and it is normalized with respect to the width or the dimension of the building perpendicular to the direction of earthquake motion we are considering. Other component is this Ri. So this Ri is nothing but the radius of gyration of mass inertia. So B upon Ri, this is also a normalized factor, and this Ri, definition of Ri is given in the code. This square root Im, that is mass moment of inertia divided by the area. So this gives us the radius of gyration of the mass inertia. The design eccentricity is again defined similar if we compare it with the previous code. So in previous code it was 1.5 ASI, so in place of 1.5 it is 1.8, and it is also to be taken in case of response spectrum method. This is a little doubtful provision, because it is understood that when we are using any of the dynamic methods, and when we say dynamic method, we mean response spectrum method with mode superposition also. So whether we are using response spectrum method or response history method, both are dynamic methods. And here the amplification of the torsional motion is automatically considered. So when we are doing a multi-mode response spectrum analysis, then the torsional amplification will be automatically considered. So similar to response history analysis, where this is considered ESI, this use of 1.8 here is doubtful. And but the code says that in case of static analysis as well as in case of response spectrum method, we have to multiply the static eccentricity, the eccentricity between center of mass and center of stiffness, by a factor of 1.8, and this 5% of B, which is accidental eccentricity, that needs to be included into that. Now, if the building is having this factor psi as less than 0.4, this coefficient, a torsional flexibility factor, is defined, which takes into account the torsional flexibility as well as the torsional eccentricity. So if this combined factor is less than 0.4, then we can design the buildings subjected to the restrictions in this table. I will come back to this table again. If the building is having psi less than, greater than 0.4, then it is not allowed. So if for any story this value of psi comes out to be greater than 0.4, then the building is called to be torsionally flexible, and such buildings are not allowed. And we have to modify the configuration of such buildings by increasing its torsional rigidity so that the psi I comes out to be less than 0.4. Now, even if it is less than 0.4, this table is to be followed. And here, two things are important. One is the ratio of torsional period to the translational period, which is representative of torsional flexibility of the building. So this ratio tau, this is the ratio of torsional period to translational period. And different ranges of this are considered, less than 0.6, 0.6 to 0.7, 0.7 to 0.8, 0.8 to 0.9. So the difference between T theta and T6, if it is more than 40%, that means tau is less than 0.6, then the building is torsionally very, very rigid. And in that case, we can design the building. If the difference reduces, it goes to less than 0.9, less than 10%, then it is not permitted. So minimum 10% difference between T theta and Ty is to be permitted. That is given by this condition. And then it is to be compared with Ek, that is nothing but equal to ESI, which we have obtained here. So maximum value of ESI we take from here, that is equal to Ek. So Ek by B less than 5%, that means less than accidental eccentricity. Here it is between 5% and 7%, 7 to 10%, and so on. So then this table is to be used. So if the building is torsionally quite rigid, then we can perform torsional analysis and design the building, until unless the eccentricity is more than 12.5%. If eccentricity is more than 12.5%, then we have to revise the design. And if the ratio of torsional period to translational period is greater than 0.9, that means the difference between the torsional period and the translational period is less than 10%, then also we have to revise the configuration. Otherwise, as per this combination of EK and tau, we can design the building. So different combinations. If the building is too flexible, then there will be restriction on eccentricity. So a combination of eccentricity and flexibility is permitted. Then the code also controls the total structural plant density, and this structural plant density is calculated as the total area of the shear wall and area of the columns divided by the plan area, width and length of the plan, and it is expressed in terms of percentage. So rho SD is giving in terms of percentage. So this permitted value, minimum value required, that is given by this expression, and this expression includes the concrete grade. So this is, please look at this, this is 2 minus 0.75 FCK. So higher grade, lesser plant density is allowed. So if we are using higher grade concrete, then this can be allowed as lower. Then n is the number of stories. This is directly multiplied. So if the number of stories is increasing, the plant density has to increase. And AHD is the design seismic coefficient corresponding to the horizontal period. So it is also proportional to AHD. If the AHD is increasing, we have to provide larger density of shear walls and columns together. Then finally, the code also provides different structural systems, admissible structural systems. So in case of zone 6, even for low-rise buildings, we can have dual systems having SMRF and special shear walls. Only dual systems are allowed in zone 6. Without shear wall, we can't construct any building. Same is with zone 5. And in case of critical structures, only dual systems are allowed up to zone 4. But here, in case of normal buildings, SMRF is, and flat slabs are also allowed. So please note that flat slabs are not allowed in zone 5 and 6. Only up to zone 4, flat slabs are allowed. But in case of zone 3 and zone 2, more structural systems are allowed. In zone 2, OMRF is also allowed. So please check here in zone 3 also, no OMRF is allowed now. So earlier in zone 2 and 3, OMRF was allowed. Now OMRF is allowed only in zone 2, not even in zone 3. So in zone 3, 4, 5, and 6, OMRF is not allowed. In zone 5 and 6, the flat slabs are not allowed. Then lastly, this new provision which has generated quite interest among our designers, that is an additional load combination where overstrength factor is to be considered. Now we have to understand what is the origin of this overstrength factor. Actually, it is in place of, or in parallel to, we can say, the capacity design approach. So in capacity design approach, we were calculating the capacity of beams, and we were ensuring that the column should be stronger than the beams. That is still there. In addition to that, this overstrength factor, omega, is also to be considered on the earthquake force. So on the calculated earthquake force, this amplification factor shall be used. Now, what is the need of such a factor when we are doing capacity design already? The need for this is there because when we were doing capacity design, let us say in case of RCC beam column frame, so we were doing capacity design to ensure strong column weak beam design. The beams were invariably taken as rectangular beams. The flanges were not considered. But we understand in reality, the flanges will also provide flexural strength to the beam. So flexural strength of the beams is going to increase, and this increase will not be there only in sagging, it will also be there in the hogging. In fact, in hogging the increase is much more, because the reinforcement which is placed within the effective width of the flange, that reinforcement also contributes to the moment capacity. Now the software available and the designer, the practice they are following, that flange reinforcement is never considered. As a result, the capacity of the beam, the provided capacity of the beam was highly underestimated. And even if we were following a strong column weak beam design, in reality, the columns were not stronger than the beams. So to take care of that, this overstrength factor has been introduced. So even if you are following the capacity design, and capacity design is amplifying the moment demand on the column, this amplification factor will not be less than 2. So whatever design force you have calculated on the beam, the design force which will be calculated on the column will be multiplied by 2. So whatever force we are getting from the analysis, that will be amplified by 2. This is expected. This again needs to be seen with examples, that whether it is able to cater for that flange effect or not. But an estimate is that the strength contributed because of the flange is of the order of 1.5. So this 2 will take care of that. So this is to be considered when we are designing columns in SMRF. So to ensure that the columns are stronger than the beams, this is required. Then beam to column and beam to wall joint, because we want the joint should not fail. The joint should be stronger than the beam. So that's another way of ensuring that. And then structural members in foundation. Now earlier the code was silent about the foundation, but now the code is clear that the capacity design needs to be done for foundations as well. And reason for that is that the foundation behavior is more uncertain. Foundation damage cannot be inspected after an earthquake, and the repair of the foundation is also more difficult. That is why the damage in the foundations is to be avoided, and that can be avoided by designing, by protecting the capacity of the foundation by suitable measures, including this overstrength factor. So foundation will also be designed for omega times, that means 2 times the forces we are getting from the analysis. Similarly, in case of shear wall design, special shear wall designs. So shear walls, in case of shear wall detailing, our current code IS 13920 is deficient, because it does not have capacity design provisions. Whereas if we look at ACI 318 or Eurocode, it has quite detailed capacity design provisions, and it will be interesting to look at those. So this I have taken from ACI 318, and what it says that first we will obtain the design forces from analysis. So whatever we are getting from analysis forces, those forces are amplified, and this amplification factor depends upon the actual reinforcement provided. So what we are getting from the analysis, that is VU, and what we have provided, that is VE, so amplified. So the amplified bending moment is much larger, and similarly the shear provided is also much larger, and that's why the shear reinforcement which is to be provided in the shear wall, that should be amplified, taking into account 2 factors. One is the actual overstrength, omega V, which is ratio of the provided moment capacity to the calculated moment demand. So actual provided capacity is much higher than the provided demand. Ratio of these 2 is omega V. And what happens due to the dynamic characteristics of the building, especially when the shear wall yields at the base, the mode shape changes. And due to this change in the dynamic characteristics, the bending moment in the shear wall gets amplified in the upper portion. And that amplification also needs to be considered both in moment and shear. So the modified shear in case of shear walls designed as per ACY 318, capital omega and small omega, these are the two factors which are to be applied on the factored shear force which we are getting from the analysis. And the maximum value is 3. This factor shall be less than 3. Capital omega is coming from the actual provided capacity. So once the reinforcement is finalized, we will calculate, we will perform a section analysis of the shear wall. We can calculate the provided capacity, and provided capacity divided by the required demand. That will give us this capital omega. Small omega depends upon the dynamic behavior of the building, and that depends on the number of stories. So based on the number of stories, this value of omega v, if omega v is less than, number of stories is less than 6, then this is 0.9 plus number of stories divided by 10. If it is number of stories greater than 6, then this is 1.3 plus number of stories divided by 30. And the maximum value is 1.8. And both omega, capital omega and small omega multiplied, the value should be less than 3. Perhaps that's the source. I'm not sure, but it appears that that is the source. In case of slender shear walls, HW by LW greater than 2. So these are the slender shear walls. Their failure is governed by flexion. So those shear walls whose behavior is or design is governed by flexion, this factor is 3, which matches with the upper limit given in ACI 318. So here this is the upper limit. Actual factor may come out to be less than this also, depending on what additional strength we are providing. So here this factor 3 matches with that. And if HW by LW is less than 1, so if HW by LW is less than 1, then this is a squat shear wall. It will fail in shear, and here actually the shear is the governing mode. And such shear walls, although rare, these needs to be designed with R is equal to 1, because these cannot dissipate energy. Only the slender shear walls where flexural hinges are forming, those are dissipating energy. Here the code defines a factor of 2. The basis of this 2 is not clear to me, and in between it is interpolating. So from interpolation, an average value of 2.5 is defined if the aspect ratio of the shear wall height to length ratio is between 1 and 2. Then axial force, shear force, and bending moment demand on these members and the combinations which are given need not exceed, I mean this is important, need not exceed those obtained by considering the overstrength plastic hinges. Now this is a new terminology. Earlier code was not using that. Overstrength plastic hinges, in my understanding, this corresponds to capacity design. So it says that this value need not to be more than capacity design. That is interesting. If I have understood it correctly, if that is the intention of the code, then this is interesting. This nullifies the effect of providing those factors, because as I said, in case of flange beam or in case of beams, the designers are not calculating the capacity properly. So if they are calculating hinge capacity, then hinge capacity also needs to be calculated for the flange section. The hinge capacity calculated for the rectangular section alone is not adequate. That is important. Or alternatively, a factor of 2 has to be used. So these are the changes in salient changes which I could find in part 5 of IS 1893 2025. We will stop here for this talk. and we can take up the question answers now.
Yeah.
Thank you, Professor Yogendra Singh ji, and it was a very informative presentation and might have answered most of the questions in the mind of the young engineers and might have raised some more questions for the professionals. We will take up questions one by one. First of all, I just want to understand this overstrain factor which has been introduced. So on one side, we are reducing the elastic force by applying R, and on the other side, we are adding back that force or we are amplifying that force for designing of some critical elements. So, how do you, explain this particular aspect? On one side we are reducing and other side we are adding back that force
Right.
and amplifying.
So actually, in case of earthquake resistant design, our current philosophy, we are depending on inelastic energy dissipation. Inelastic energy dissipation can take place only in certain members in certain modes. For example, when we are talking about RCC buildings, inelastic energy dissipation can take place in beams under flexure, because when we add axial force, the ductility reduces, and
Right.
as a result, the inelastic energy dissipation will be less. So in case of columns, the inelastic energy dissipation is very minimal. Similarly, in case of shear wall, the inelastic energy dissipation can take place in fractional yielding at the base. If the failure occurs in shear, then in shear wall also we cannot dissipate any energy. So we want that the structure should yield, and we can take advantage of that using response reduction factor. But at the same time, those modes or those components which are not ductile, those should not fail. So this
Right.
overstrength factor or capacity design, this is to ensure that those components or modes which are non-ductile, those should not yield, those should not fail. Because if those get triggered, then our energy dissipation capacity will be lost. So we want the desirable components to yield and undesirable components not to yield. That's why both these contradictory appearing steps we are taking. We are reducing the force while designing ductile components, and we are increasing the force again to avoid failure of non-ductile components.
Right. So we are avoiding the brittle failure. Yeah.
Yeah, to avoid the brittle failure.
Thank you, sir. So we'll go back to the questions. There's one question. The old seismic code says that the seismic design we plan, that seismic design we cannot design the structure to resist the seismic forces because of actual seismic forces are cannot be determined. But in seismic design, we used to make the delay of the collapse of structure during the seismic action. In this new code 2025, seismic forces are very high. That means we are designing the structure against actual seismic forces.
No, perhaps this understanding is not correct. The old code and the new code, the philosophy is same. As I said in the beginning, there is no change in the philosophy. The actual earthquake force in both the codes is much higher than what we are designing for. We are designing for a force reduced by a response reduction factor or elastic force reduction factor, which is of the order of 5. So we are designing only for 20% of the elastic force in both the codes. And it has been our continuous effort to estimate the realistic earthquake force. So as our understanding, our knowledge of earthquake phenomena is improving, we are improving the estimation of earthquake force. So that's why this response spectrum, JAD value, the zonation map, it is continuously improving. But now it appears that it has reached up to a level where not much changes will occur in future. So if we compare, perhaps Dr. Vijay will compare, if we compare the previous code and the new code zone factors for the same written period, that is 2475 year. So previous code in zone 5, which is the highest zone, it was 0.36 into 1.5, that is 0.54. And in the new code, it is 0.7. So that much jump has taken place. It is already, people are debating that this jump may be more than the real, or it is real. So that debate is going on. But at least we have reached the range. Now it can't be increased. It is not going to increase further. So that type of changes are not expected. So we have reached a level where we have estimated the realistic earthquake forces quite reliably now. Earlier, we were intentionally and unintentionally, we were underestimating earthquake force. Why we were underestimating? Earthquake forces intentionally, because earthquake resistant design is like an insurance cover. If you want to cover more, you have to pay more premium. So to keep the cost, the country was poor. To keep the cost of civil construction lower, the earthquake forces were estimated intentionally lower. Now that thinking has gone, and we are trying to estimate the actual, real earthquake forces. Mr. Kulkarni?
Yeah.
Are you able to hear? It looks like
Anand, I think he has. I'll continue. So we'll take from start actually to 12 p.m. Which time period is to be taken for calculation of vertical earthquake? As with 0.4 seconds, it is substantially higher, and if load combination of say 1.5 TL EQZ plus 0.3 plus 0.3 EQI to be used, along with three-dimensional earthquake load combinations. Also, actual load in columns, etc., increase substantially. Can we use modal time period for now, or we have to use the?
We can use modal period in any case, but getting vertical modes excited is quite difficult. Generally, we will not get vertical mode time period, and even if we will get, that will come out to be less than 0.4. So in vertical direction, buildings are quite rigid, and invariably it will come out to be less than 0.4, even if we are performing modal analysis. And I understand by modal analysis, the person asking question does not do not mean that it is horizontal period. Horizontal period is longer. The vertical period is quite short. The building in vertical direction is quite rigid, and that's why the code does not talk about period. It has given a factor of 2.5, because obtaining the vertical period may be difficult.
Thank you, sir.
Arun, you can take a few more questions here.
Yeah. We'll take, I think, five questions. That is better. So we can decide that. So in overstrength factor load combinations, shall we use 1.25 FY? Because this load combination will always be higher than 1.5 DL plus RGQ combination.
No. So this is to be designed. I mean, the design capacity is to be obtained in the same manner using the normal limit state method. No other factor. Only in case of soil, the code allows an increment, but not in case of building components.
Yeah. Next question is, can you please clarify in comparison with 2016 version, which load combinations should be used for sizing the foundations as per part 1? So I could not get it actually.
Yeah, no, I get the question. There is a problem. Because in foundation, when we are doing the designing, there are two designs. One is the structural design, another is the geotechnical. Geotechnical design is working stress method. And in our code does not talk about, I mean, this code does not talk about load combination for working stress method. So, sorry, it talks about load combinations, but there the earthquake is different. So we have to use, I mean, two possibilities are there. One possibility is that the same earthquake, we use a reduced load factor, or we use working stress method, or the load combinations corresponding to
Working
serviceability earthquake.
Yeah,
So
correct.
those load return periods, which corresponds to working stress method of the same importance category, those will be used for sizing of the foundation or any other working stress design.
Yeah, right. Thank you. One more question is, for assessment of liquefaction potential, which table is used to find design return period? Table 1 or table 2? Any?
Yeah, that is a tricky question. The code perhaps does not answer that because liquefaction, whether it is consistent with working stress method or it is consistent with limit state method. I guess it is consistent with working stress method, but I'm not sure. Truly speaking, I'm not sure. I have to discuss it with my geotechnical friends. Then I can come out with the answer.
Thank you, sir. We'll,
Hello.
Yeah. Hello.
पुनीत भाई तुमको बाद में फोन करता हूँ. I am in the middle of meeting.
Vijay,
Yeah.
please mute yourself.
Yeah, okay. Yeah. One more question I'll take and then hand it to answer. Sir, while calculating shear wave velocity, the weighted average to be calculated from ground level till depth of influence or
Right.
from founding level to depth of influence. That is a very crucial question for basement structures.
It is from the ground level. Code is very clear. It is from the ground level.
Even
Not
for large basements?
Any. It has to be from the ground level.
Ground level.
Actually, it is the top layers which are modifying. In my opinion, it should have been only the top layers.
Yeah, correct.
Whatever is the depth of the embedment, that doesn't matter.
But the wording means, I also read that wording. Wording almost intends that it is from founding level. Like, means it is not specifically saying that. I understand that it is to be ground level, but for basement structure or maybe for it will create a lot of difference. But
Yeah,
it should be at
a
ground
lot
level.
of difference, but
Yeah.
it should be. Even if the code says otherwise, that is an error.
Yeah.
Because actually, irrespective of the depth of the foundation, it should be top 30 meters. So site classification is done in free field condition, means there is no structure. In that condition, what will be the ground motion at the surface? That is to be considered.
Thank you, sir. Anand, you can continue.
Yeah, Arvind, some of the questions are not seen on my dashboard, so I'm just taking from the latest one. I'll go. And,
Okay. I will
so
continue with the
sir,
earlier one.
Yeah. So there's one question which asks that are we required to consider soil flexibility, that is assigned springs in the model for analysis and design of superstructure while we analyze the superstructure?
Yeah, code says that whether you analyze superstructure or substructure, you consider.
You need to that, yeah.
Soil flexibility.
Okay. 1 second. Okay. Regarding geotechnical asset, as per the clause 9 of IS 1893 part 1, please explain the flexibility of soil that is to be considered in foundation. Modulus subgrade reaction is used. So are we no more taking full fixity at the bottom of the while designing of the building?
Yeah.
I think these two things are different. Yeah.
Current design also, two approaches people are using. Some people are assuming the bottom point to be fixed, and some people are using the bottom point to be pinned. And the reason is uncertainty about the fixity provided at the base, and which one is conservative. So as far as the column design is concerned, the pin assumption is conservative. But for the design of the foundation, it is the fixed assumption which is conservative. So currently also we were insisting on both the assumptions, in one case fixed and another case pinned. Now the code is saying that you take the realistic, and reality is somewhere in between. So if we do not know reality or we do not want to estimate the reality, then we consider extreme condition, and extreme condition is pinned and fixed. But now the code has provided realistic values of fixity which are to be considered. So the foundation should not be considered as fixed. Rather, whatever fixity the code is suggesting, that fixity or that flexibility should be considered.
Okay. So there's one question, the meaning which I could get from the question, that it looks that the gentleman is from Jammu and Kashmir, and he's asking why this is now classified as Zone 6. Can you elaborate the Himalayan tectonic processes that lead to this classification?
So actually, I am not a seismologist, so I will not be able to exactly pinpoint, but we understand the whole of the Himalayan region, lot of seismotectonic activities going on, number of faults are there, and this is known to be one of the most seismic areas of the world. So that's why this was expected. Earlier, the seismic hazard in Himalayan region was lower. It was estimated lower. And as I said, that to some extent that was intentional. Now we are going to the realistic. It will create a lot of problems because a lot of jump is there. Design will be difficult. Many problems will be there. But the code has tried to be more realistic. But
There's one
exactly which
question.
faults are there and
Yeah.
what is the potential of different faults, that question I can't answer. Maybe a seismologist can answer that.
Right. Okay. There's one question which says that if the beam is designed with the advantage of the flange, should we still consider the overstrain factor to uh, consider it additionally?
In my opinion, no. But the code doesn't talk about flange, so it's unclear what is the intention of the code. Is the intention of the code this, that people will be designing in any case without the flanges, and that's why this factor of 2 is to be applied, or code has some other consideration? It's not clear. But in my opinion, if one is following capacity design principle, including flange, then overstrength factor is not needed.
There's one question which is asked by many participants, that if all the old buildings which are designed as per the previous code, 2016 version of the code, uh, do we need to recheck the design or assess the structural safety by applying the new codal provisions?
Code doesn't say anything about that. So this is actually, code is dealing with the technical issues, and this is more of a policy issue. So that is to be decided by the local governing body or the owner. It is not to be
Yeah,
designed, not to be decided by the code.
so over to you, Arvind.
Yeah. Next question is in this revised code. It seems that in clause C 2.8.1, deterministic approach has been used in place of probabilistic approach, where they get low values. In the attached PSHM study, Chennai gets a low value PGA of 0.03 for written period of 475 years, but new code by deterministic approach has arrived at 0.125. Because of a conservative approach of code committee, Tamil Nadu has got more PGA values.
I'm not an expert in that, so I will not be able to answer this question in detail. Okay. If it is regarding Chennai, then you are recommended to contact Professor Raghukant, because he is the person behind this exercise. He did this PSH exercise, so he can better answer. But in my opinion, they have not been conservative. I mean, they have not decided to be conservative for any region. Whatever values they were getting from PSHA, based on that, this hazard donation has been done. And as far as I understand, seismic hazard assessment is still not very precise. Different people come out with different answers. So this value which you are getting at 0.03, they may get it different.
Thank you, sir. Next question is slide 70 of your presentation. R equal to 1 for vertical direction, since we can't have hinges in the columns. But vertical force will also cause hinges to form in beams. Could you please discuss? That is what is wanted. We wanted.
Yeah, but that will not see. When we are considering the vertical force which is acting on the beam is limited. Most of the vertical force is acting in the columns, because in columns it gets accumulated. In beams it does not get accumulated. So that is why that dissipation of vertical energy or energy under vertical excitation will be much less through the beam.
Sir, in continuation with that, I wanted to ask whether means this vertical, you said it will be move as rigid, but what about the cantilevers at say higher levels?
Sorry, I have not covered that, but the code covers that.
Yeah, okay.
I have skipped that, but the code covers that how the horizontal and vertical cantilevers will be designed.
Okay.
So it says, because it is not assuming any amplification of vertical component along the height. So it says that you calculate the vertical acceleration, which will be same at all the component, all the floors, and design these for vertical projection, horizontal projections for that force.
Thank you, sir.
But response reduction factor is 1.
One. Thank you. Next question is, in case of rocky strata, where RQD and TCR is used in geotechnical investigations, what is the method to estimate shear wave velocity?
Shear wave velocity can be estimated using geophysical methods like MASW.
He means to say when the specific tests are not there, what normal soil investigation, like there is a n value. I don't think there is any method for that.
You can't do that.
Yeah, correct. Next is, Professor, as you said, in the vertical seismic action, the response reduction R should not be considered the plans occur in the columns, which will respond for the horizontal, that is already we have covered. But as an intermediate structure, the beam joints also will have plastic hinges. As can we consider the R factor for the vertical seismic action? We have just covered that.
We just covered.
Okay. Sir, that gather that importance factor is included in zone factor. However, clause 8.2.2 is referring to respective IS 1893, that is say part 4 for industrial structures. Please clarify on it.
Okay, so the major classes of importance, that is 1, 1.2, 1.5 and 2, those have been included in return factor. But theoretically, hypothetically, if there is any other structure which lies in between, let us say 1.35, somebody wants to design, that is not covered by this. So for that, the code may provide. But as far as building code is concerned, I have explained that all the importance factors are 1. That means importance factor is not there practically. Code has retained it just for some hypothetical or unforeseen cases where something like this can happen, and somebody wants to tweak a little bit the seismic design forces. For those cases, this concept of importance factor has been retained. But in the previous sense, it is not.
But sir, that is correct, but that is going to create confusion till the 2000. So in the part 4 is come because there are that is not that terminology is not there in part 4, and there is an importance factor. And
I agree.
Then hazard assessment will give some additional force, and then there will be importance.
I agree. It is creating a lot of confusion in bridge design. Because in bridge design is done as per IRC code, hazard is being taken as per IS 1893, so a lot of confusion.
Same is going to be with the industrial structures also.
Right. So one has to understand that what is the basis of this. So importance factor is included. So that is only for theoretical regions that clause has been written.
Yeah. Next is which elements frames to be considered for additional load combinations specified in 14.4. That must be that overstrain factor.
So which components are
which elements or frames? Only columns are to be considered, correct?
No, columns are to be considered, beam column joints are to be considered.
Yeah, okay. Thank you. Over to Anand.
Yeah. Okay. In line with SLS checks from IRS, IRC codes, how do we incorporate parameters from IS 1893 2025 if the value of IS 1893 is talking majority about ULS aspects?
So this check for earthquake under
SLS
SLS code.
checks.
SLS checks are there only in IRS code. No other code has earthquake checks for SLS. So I was discussing with some of the metros, they are facing this problem. So there we can take it, see how this concept of serviceability DVE MC came. So first, all the designs were done using working stress method, and earthquake was estimated corresponding to serviceability. So serviceability level earthquake was being designed for, was being considered for working stress method. Then we started limit state method. The limit state method that is estimating capacity roughly 1.5 times of what working stress method is calculating. For example, in working stress method, we are using permissible stress in steel as 0.6 Fy. In limit state, we are using 1 over 1.1, so 0.9. So ratio is 1.5. So this ratio 1.5 is very interesting in earthquake resistant design. It appears again and again. So accordingly, the DVE was defined as 1.5 times of serviceability earthquake. So ratio between DVE and serviceability earthquake was 1.5. So this same 1.5 ratio we can take there. So when we are doing serviceability check, we can take the load factor 1 over 1.5. And that we can use for serviceability.
In current case, we are using one stiffness modifier as 1 for shear design, but in new version, different factors are provided. Please explain.
No, factors are same. Only
Same,
thing
I
is
think,
that
yeah,
how this is calculated. So previously it was 1 times G into A. Now it is 0.4 times E into A. So this is ratio of G and A. So when you are calculating shear stiffness depends upon GA. If you are calculating with respect to EA, okay, then that factor is 1.4, sorry, 0.4. So that's why it creates confusion. Otherwise, it is full in both the codes.
right. Do we need to use different modulus of subgrade for analyzing wind and gravity load cases, and different for seismic case?
No, currently code doesn't say that.
Okay. Over to you, Arvind.
Yeah, thank you. Load combination in clause 8.4.1, load combination is 1.2 DL plus 1.2 IL plus minus EL for LSM. And for WSM, it is 1 DL plus 1 IL plus minus EL only. Why EL is not reduced in WSM by factor of 0.7 as per
It is
our
actually
philosophy?
reduced because the EL which is given in working stress method is for a different return period. That return period is much lower.
Okay.
So actual EL is reduced. Both the EL are not same. So please keep in mind that the EL which is given in working stress combination and the EL which is given in limit state combination are different.
Thank you, sir. That's very important. Yeah. Next is as per earlier code, maximum scale factor along X and Y direction shall be used for vertical scale factor. In present code, it is not mentioned. Please clarify. What is scale factor?
Oh, that was incorrect understanding previously, that scale factor BV bar by BV correction.
Yeah.
So in vertical direction, you need not to apply any correction because we are already using SAYG is equal to 2.5. So we are considering in the maximum range. So no scaling in vertical direction. Scaling will be required only in horizontal direction.
The old seismic code says that in the seismic design, we cannot design the structures to resist the seismic forces because the actual seismic forces can't be determined. But in the seismic design, we used to make the delay of the collapse of the structure during the seismic action. But in new code, seismic forces are very high. That means we are, yeah, that we,
discussed.
That I
yeah,
think
we
we have
discussed
taken.
that. That
Yeah,
is,
we
we have
discussed.
discussed, yeah. Sorry. Uh, the return period 9975 years represent what state of earthquake, special or very severe condition?
So
What?
9975 is much more rare.
Hmm.
Okay, earlier it was used in design of dams and nuclear power stations. So in that type of structures we were doing. Now a special class of buildings, although to me it is not entirely clear from the code that which types of buildings will be really those buildings. So it is strategic importance, buildings with strategic importance. So those buildings will come in this category. Even hospitals are not in that category.
Thank you, sir. Now, this is a very general questions, but most of the people are want to know that now the revised code is introduced. When will be the code will be used in practice? There is no broad guidelines about revised. That is nothing to do with code. We have to decide that.
Yeah. Whenever we will start using it, it will be used.
Correct.
I think there is when the old code is getting withdrawn,
Yeah,
I think
yeah. There is a
that
there is a gazette notification that old code will be withdrawn in May 2026. So before that, we have to do that.
yeah. So once it is withdrawn, I
Hmm.
think we cannot use it for new buildings at least.
Yeah, at least.
That's what my understanding is there.
Yeah, that's correct.
Yeah. Next is what is the basis for considering 2.5 times design horizontal acceleration for estimating VBD for portion B as it gives almost 3 times base shear?
No, it is not 2.5 times horizontal acceleration. It's 2.5 times vertical.
Vertical acceleration.
So 2.5 is basically the SA by G in current terminology.
Yeah. Next question is related to the shear wall and slab combination. Is it mandatory to provide beams at floor levels along with shear walls, or can the slabs be supported on shear wall directly with reference to 2026? This is directly putting the questions on my one building, sir. I think.
Yeah, so it looks like that those buildings have been removed.
Removed,
from
yeah,
the-
correct.
Yeah.
So that is a
Code
very, very,
clearly- code
Yeah,
very
very,
so-
clearly says that
yeah.
those cannot be used.
So does it mean that the code limits the applicability of the provisions for this kind of buildings?
Yeah.
Right.
Does it mean that all these buildings will need performance-based design?
Yeah. I mean, the code simply says that this code cannot be used. Then which is the other code? There is no other code.
There is no other code. That's what.
There is no other code.
So that is a being a very lot of questions in at least in urban that is Mumbai,
I
Delhi.
mean, code was meaning earlier also the same thing, but
Mhm.
it was not explicitly written. Now the code has explicitly written that those buildings are not covered. Earlier, people were using with some if and that they were using.
One more
Even if
question.
there is even if there is a beam, sorry, the beam slab and wall system, but if we use few coupled walls there, with some beams to in either directions to take those lateral forces, and we design those for only those elements for carrying all the lateral forces. Will it
No, I
be?
don't. Code means that. Code means that you have to use frame and shear wall combination. Just shear walls you can't use.
Okay.
Next question, portion A and portion B, when need to be considered? So it is for basement, but how is there any definition of that basements? How much more area it should have along, or there can be straight basement also can be done that.
See, if it is embedded in soil,
Yeah.
its stiffness is going to be much higher than the top portion.
Even with the same area.
Even with the same footprint.
Yeah. So it has to be. It can be considered at any time. If there is a basement, we have to consider.
If it is embedded in soil, then in all conditions. Only in one case I don't foresee that, when the tower is separated from the basement through expansion joints.
Yeah.
In that case, it may be.
Thank you. Over to Anand.
Yeah, you can continue. I think
okay.
you can continue
Okay.
and complete the session. Yeah.
Okay. Hi. Okay. How the new zone values are arrived for new code based on return period? It is simply said that 50%, 56%, 46%, and 20% increase in values given for Z values in 2016 code has been obtained in 2025 code.
The question is not clear.
Not clear how.
How
Actually,
the
we
return
have.
periods have been obtained. Perhaps question is this.
Yeah, must be that different return periods, but means that we have already actually answered in the earlier thing how
Yeah,
it is calculated.
I try to explain
Yeah,
that it is related with the importance factor.
Importance factor. Permitted in future. The same thing, structural elements like pure wall and slab systems are extensively used in residential period. Shouldn't this system be permitted in future as well? Yeah, or there is separate provision.
No, that is
So
required.
that,
Actually, in industry, I mean, this is a very important issue. In industry, several constructions are going on. This is one. Taiwan is one, which is very extensively being used. Another is this composite construction or RC column, steel beam, and different types of composite combinations. Those are being used. The code says that pre-tensioned slabs are not to be used, but these systems are being used in industry.
Yeah.
So something has to come out. The code has to come out on that. Whether it may be that these are not to be used at all, we should stop, or something. Just by saying that code does not cover does not serve the purpose.
Yeah. Next question is also related to that. But the questioner has already said that structural systems specified in 1.2, 2.8 and not covered by code has performed very well in past earthquakes. Most Chilean buildings are of these types. That is the information. So next is why serviceability check for deflection is not considered necessary under EQ condition as per new code that we have already explained. This it is earthquake is a not
a serviceability criteria.
Is any book on revised 2025 is expected soon for engineering students to follow the new code?
I do not know. At least I am not writing, so I do not know if somebody is writing.
But is there any commentary is expected? What you are saying
is
again?
That is being discussed again and again in the code committee that we have to write a commentary. But still,
yeah, I think
we will be writing that it's not a streamline. I mean, it is not chalked out.
Then next is how should the stiffness modifiers for shear recommended in new code be accounted for analysis modeling in ETABS or SAP? Please provide guidance. Generally, such shear stiffness modifiers are not explicitly specified in international codes. Please correct me if my understanding.
There is no modifier. That's what I explained.
Yeah.
That actually there is no modifier.
Some misunderstanding.
Some misunderstanding.
Design based shear, how the 50-meter building height criteria is defined without considering the plan area. Is that because it's whatever the plan?
There cannot be any theoretical calculation of height beyond which we will consider it tall, and this is just a policy, a protocol, or a judgment, we can say.
There is one interesting question. Below block foundation, there is a 4-meter thick PCC layer overlying natural soil. While calculating the weighted average shear wave velocity of the soil profile, is the PCC layer to be treated as a soil layer or should it be excluded from the VS calculations? What is the correct approach?
Okay. So actually, when we are talking, see, this amplification or site classification, that is based on seismic waves. Wavelength of seismic waves is much larger. This is small PCC for seismic wave, this is small. So wavelength of seismic wave is 500 meter or more, in that range. So this is nothing for that. So it is not going to affect earthquake at all. So this should not be considered.
Yeah, thank you. These are the torsional flexibility requirements specified in this code applicable to buildings with height greater than 50 meter also?
Should be.
No. But then you are saying that now they are exclusive codes.
They are excluding that, but I mean, any
So I think,
good thing of one code should be applicable in the other.
yeah, some of the conditions additionally they will be applicable for all tall buildings, means above 50
Yeah.
meters. So
So
that
similar-
doesn't mean that, yeah,
Yeah.
it is
please
over
carry.
and above 1893, what we
That's
can
why
say.
those codes, those clauses which are in contradiction with 16700, the code has explicitly written for buildings less than 50. But in
Only
some
for those clauses, not for overall
those
code.
clauses, it is to be excluded. Other
Yeah.
clauses which are to be applicable for tall buildings also, code has not given any qualification.
The similar question is there in mind as regarding IS 16700 time period. That time period 1670 says it should not be more than that.
Yeah,
But
period should not be longer than that.
Period should longer than the certain
Yeah.
method. So does it mean that if the 1893 period, whatever is calculated, if it is less than that, which is to be considered?
No, I mean for tall buildings, the period formula is different.
The formula is different, but that is saying only that formula is should that period should not be more than that formula. It is not saying it should not be less. Maximum limit IS 16. Yeah.
Maximum limit given for calculation of base shear. So that means the base shear which is calculated as per that formula, the base shear should not be lower than that base shear. Actually, it means that.
Yeah, correct. But the time period as per 1893 comes lower than that for tall buildings, then the base shear will be anyway.
It is not to be checked.
It is not to be checked.
Period is not to be checked.
Not to be checked. Okay, fine. What is the empirical formula to be used for fundamental time period estimation for braced steel frame buildings?
We have to look at, I have not gone into that part, but there is a section 4 of part 5, which is about steel buildings that will provide.
I think we should take
Yeah.
last three questions
last
finish
three
this at
question.
5:30.
Yeah. Correct. We'll at 5:30 we'll stop. My question is, the Indian code gives us suite of 30 ground motions based on different zones and near field and far field motions. Do we have to run the analysis for all the 30 suites of motion or 11 motions as per ASC?
No, not even 11. If you are doing linear analysis, I mean, we have to check those ground motions have not yet come out. I mean, once we look at those ground motions, we will check whether those are spectrum compatible or those are natural recorded ground motions. If those are natural recorded ground motions, then we should use 11. If those are spectrum compatible, then even 3 are enough.
And whether we can use other motions apart from BIS suite of ground motions from peer NGA based database with appropriate
I mean, more than that you can do, but at least 11 ground motions you have to take from there.
Generally, the thickness of walls or grade of concrete are changed or reduced along the height of the structure. Does the structural plant density need to be checked at the upper levels as well?
Yeah, and that's why the N there appearing is above. The story is above that level.
Each level you have to do that, wherever it is changed. In structural wall design, the demand capacity ratio for flexure is often relatively high. In a hypothetical scenario where the flexural DCR of a wall exceeds 3, the worsening factor used for shear design would still remain 3, as recommended by the code. What would be the considered better practice in such a case?
In my opinion, better practice is capacity design. We calculate the actual demand which is occurring, and we should ensure that capacity should be more than the actual demand.
I think we should
I think
conclude.
we will take the questions after Dr. Vijay's lecture. Balance questions we can take after that. I'll hand over to Rashmi.
But wait, what we
Yeah.
can do is assure all the participants
Yeah.
that there might be still few questions unanswered or new questions coming.
Yeah.
They can mail it to us. We can forward it to Yogendra sir and get
Sure.
answered by email.
Yeah.
Or if questions are too many, Yogendra sir, we might have to have only question answer session.
Once again. Yeah.
Once again.
Yeah.
We'll look into that.
Yeah.
So that
Right, we
everybody,
can do that.
Yeah.
because few questions are coming to me on phone. So I said, I cannot interrupt now. So thank you, sir.
Yeah, thank you, sir. We are over to Rashmi.
Thank you, sir, for the wonderful session. I think there are too many questions are still unanswered. As per Jen sir said, we can have one separate session for the same. Now I would like to wait a minute.
Dr. Vijay Khose.
Yes,
Yeah.
yes. Just give me a minute, sir. Now I would like to invite our next speaker, Dr. Vijay Khose. He is a PhD earthquake engineering. He is a PhD in earthquake engineering from IIT Roorkee. He has 13 plus years of professional practice, structural design, and peer review of complex buildings. His core expertise in high-rise commercial and residential towers, advanced lateral load resisting systems, seismic and wind-governed design, performance-based design, and retrofitting. With India, he has project experience exposure in USA, Turkey, Middle East, and have strong understanding of regional seismic demands. His proficiency in Indian, American, and Turkish seismic codes, known for innovative code compliant solution. Dr. Vijay sir?
Yes, thank you.
Yeah, over to you. Thank you, sir.
Thank you.
Welcome, sir.
Can you see my screen?
Yes, it is visible.
Okay, so thank you everyone and good evening. So this is webinar 150 related to IS 1893, which is released in 2025. So I will be talking on impact of IS 1893 Part 1 and Part 5 on the design of especially RC buildings. So I will take a quick minute, like those who are not aware, like what is Tantan City. So we are MNC, we have offices across the world. In India, we have 3 offices, Mumbai, Pune, and Chennai. And we are like structural consultants providing different solutions related to structural design. And these are our like some of the stadiums that we have designed and some of the tall buildings that we have designed. So with this quick introduction of Thornton Thomas Electric, we'll start with the impact. So sir have already explained this, like there will be 11 parts of the IS 1893. So this restructuring is being done, like some of the codes are like already released and some of them will be releasing, and these 11 parts we will also have in like 13920 as well. So parallel part of this will be there, and again there will be another for the evaluation and strengthening will be also another code. So again there will be these 11 parts. So with this new code, so let's first understand like what is the change, what is the change in workflow, like how we were calculating design seismic force before and how we are going to calculate now. So in earlier version in 2016, we used to do like determine the seismic zone, then soil type, and based on that, we used to select design spectrum, and we used to estimate time period, and then based on that, we used to get like SA by G. Then depending on the category of the structure, like there were three categories, we used to select like what is the category and corresponding importance factor. Then depending on where is the building, like how tall, we used to select the structural system and corresponding R factor. And we used to calculate the seismic weight. And after doing this, we used to get unfactored base shear. So I would like to underline the word unfactored. The whatever VB we were getting in the 1893 2016 version, that was unfactored base shear. And then we were checking with the minimum base shear and seeing whether that value is more or less, and whichever is maximum that we used to consider. And after that, in the load combination, we used to uh, multiply it by one. Earthquake load was multiplied by 1.2 or 1.5. So whichever combination is there. But then after calculating that, we used to multiply it by 1.5 or 1.2. That was the load factor. But in the new version, so there is some change. So change is now we determine seismic zone, soil type, design spectrum. We used to select based on zone and based on soil type. We used to select the designs. We are going to select design spectrum. But after that, we have to identify the category of our structure. And based on the category of our structure, we are going to select the return period. And once we get the return period, then with that help, we can uh, like calculate the forces. So the next step would be like then estimate period and corresponding ASD. ASD is the spectral acceleration, that design spectral acceleration. So with help of the return period, we can get this. Then this is same as like earlier version, select system and response reduction factor, then calculate seismic weight. And whatever base shear now we are getting is now factored base shear. So we need not to multiply it by a load factor. And if you have noticed, so there is no load factor in the load combination. And then we'll check with minimum base shear. And once we finalize what is our governing base shear from the factored base shear and minimum base shear, then we are going to like amplify this base shear for the overstrain factor. These overstrain factors for the lateral elements design, that is only in shear, and for foundation, uh, we have to use this overstrain load factors. So that we'll discuss later. But I wanted to emphasize the workflow has been now changed as compared to previous version. Uh, now, coming to seismic zonation map and zone factors. So we know like there has been addition of one zone, that is zone 6. And if we see the India, so you can see like almost all the states are like affected by this change in seismic zonation map and addition of seismic zone 6. So there are some states where there is a reduction. For example, Lakshadweep. So from 3 to 2, it has been changed. And there are like states like Bihar, you can find like now there are all the zones present. Even you can find in Punjab also, there are all the zones are present. So if we see like city-wise comparison, so there are the some cities like for example Almora, Bareilly, Chandigarh, Darjeeling, Dehradun, Gangtok, Jaipur, and many others. So you can see the zone has been revised, changed to by 2 zones. So earlier, for example, there was zone 4, now it is zone 6. So the seismic demand has been increased significantly. There are some cities where zone has been downgraded from like, for example, from Ahmedabad from 4 to 3 and other cities as well. So next comes is like categories of structures and design period. So here we can see there are 4 categories now: normal, important, critical, and special uh, s- structures, and corresponding return period have been provided here. So for us, if we are using limit state design of method, then we'll have to use this period. If there is some design where still we are using working stress method, there we can use this uh, return periods. And how to classify these categories? So if you refer to table 1 of IS 1893 part 5, there you will find they have provided descriptions, and wherever your building is fitting into, you can choose appropriate category. So now earlier we used to get like only like 4 zone factors, and that was given for the MC level, and corresponding period was like 2475. So now since we are providing return periods, so for corresponding return period, the zone factors have been provided. And this is given in table 3. And in table 16, you can find the multiplying factor. So this factor, like the zone factor is given at 2475 return period, and corresponding, like you multiply this factor, you will get the uh, zone factor for corresponding return period. So if we compare this with the 2016 version, so let's take a building category, normal, and there for normal building category, the importance factor is 1, and the return period uh, for like this category as per 2025 version is 475 years. So what was provided is the zone factor 0 0.1, 0.16, 0.24, and 0.36. Since there is a no load factor, so and in load combination, the load factor for the earthquake is 1. So I am considering 1.5 into that zone factor. So that will give us 1 value. Now, if we multiply further by 1, that is importance factor. So that will give us the uh, zone factor plus load factor plus importance factors. And for designing, we used to use like Z by 2. So I am dividing it by 2. So now this is what we were designing for after doing all the load factors, importance factors, and dividing it by 2. So we were getting design basis earthquake, and that Z value for that is coming this. So if we compare with this version, then we will see that the in zone 2, there is no increase. In zone 3, there is like 4.17%. In zone 4, there is like around like 29%, and in zone 5, there is like 23% increase, and there is the addition of zone 6. If we take like important category, so corresponding importance factor for 2016 version is 1.2, and return period as per 2025 version is 975 years. And if we compare these numbers, then we will see the change. How much is the change in the force? So we can see it's between like 11% to close to 30%. The next category is like critical. So where importance factor is 1.5 and return period is 2475. And there you can see the change is around like 23% to 39%. Sorry. So next is site classification. So in site classification, if we see, there are different parameters used for the site classification across the world. So if we see ASC 7, there were like they are using 3 parameters: average shear wave velocity, SPT value, and unconfined shear strength. And similarly, Eurocode is also using like similar parameters, but it give preference. Like let's say you have all 3 parameters, which should be used first. And similarly for New Zealand code, they are also using like in addition to these 3 parameters, they are also using the low amplitude natural period, then low amplitude natural period based on shear wave velocity, and low amplitude natural period based on Nakamura's ratio or recorded earthquake. So if we see like 2016 version, so that was only classifying soil based on the SPT values. Now there is an addition, like we can primarily use the shear wave velocity, but there is the option to use SPT values as well. And we'll see like whether we can use it or not. And the classification is like A, B, C, D, E. So basically E is not preferred site class. We'll have to do ground improvement for that. So let's say we don't have shear wave velocity. And in that case, we can use these conversion factors. Let's say we have SPT values. So here, there are certain criteria. If we meet that, then we can use this shear wave velocity conversion equations that is already specified in the code. So the condition is normal structure in all earthquake zones. We can use this important structure in earthquake zone 2 and 3. For these, we can use this conversion factor. But in this, there is condition: if your SPT value is less than 10, then we need to use shear wave velocity. So this option is there, but we'll see whether we can really use this or not. So if we are doing this for like dry sands, then you can see you are like supposed to fall into category C or D. You cannot go into category A or B because these values are very high. After using these equations and like converting this to like what number we need to achieve that upper limit or lower limit. So this is the limit. So in this, using this, you will fall into either C or D category. If we do for the like saturated sand, then we will either fall into C or D category. Again, if we do for clays, then we will fall into category D only. So that is the penalty if we are using these equations without using the shear wave velocity. So if we compare the classifications of different codes, we can see like we are like closely matching with the ASC 7 site classification. And based on this, we can see how our classification is falling into. So you can see our ASC 7 class and IS 1893-2025 class, they are matching. But then if we are using the classification as per the SPT value based on the shear wave velocity conversion equations, then we are always going to fall into like either C or D category. So the change is soil is now classified primarily based on shear wave velocity, and the impact is like project will now require additional geophysical testing to measure the shear wave velocity, and the revised site class based on the shear wave velocity will increase the design spectral acceleration and base shear. So we have cases where like our site class was type 1 based on the SPT values. And when we do like SPT, shear wave velocity testing and got the numbers, our site class was like type C. Then next is a response spectrum. So in the response spectra, we'll see the old code and new code. These numbers has been revised. For the type 1, it is like same. There is no change in the corner period of this, but then other type or type site class C and D. So when I am saying type 1, that is site class A and B, and type 2 is site class C, and type 3 is site class B. So this is how I am using those terms. So uh, these periods have been revised. So the other important thing is like earlier, there was only spectrum was provided up to only 4 second, equation was provided up to 4 second, and there were no like values beyond that. It was allowed to consider whatever value as like 4 second that can be used for the up to 6 second. Now the corner period has been uh, defined between the velocity control region and displacement control region to 6 seconds, and the spectrum is provided up to 10 seconds with a clear definition of displacement control region. And these are the different equations, like old one and new one. So in old one, you can see this range was displacement control region was like 6 divided by TH square for site class A and B. And similarly for other class were missing. So that has been included. So what does that mean for us? So we can see here these solid lines indicate the old code and the dotted lines indicate the new code. So you can see the class 1 or type 1 and site class A and B, they are like matching up to 4 seconds. And uh, beyond 4 seconds, so that was like constant line going up to 6 seconds. And but in this new version, since there has been spectrum has been extended up to 6 seconds, there is a, you can see, decrease in the acceleration, and beyond that also there is a decrease in acceleration because this corner period is now defined and this equations has been provided. So from this we can see beyond 4 second in like type 1, that is A and B, and in 4.5 second, close to 4.5 second in class C, and like close to, I would say, like 4.8. So beyond this period, you can see there is a decrease in the spectral acceleration. So, and if we see the soil amplification factor, so earlier uh, there was in the acceleration control region, there was no amplification. And here also there is no amplification, but then in the previous lecture, sir has already uh, confirmed that like this has been already considered in the zone factors. But in velocity controlled range, if we see the earlier amplification was 1.36, now it is 1.5. So there is close to 10% change or increase in the demand. And in like type D soils, there is like close to 20% increase. If we see in the displacement control region, so since it was not defined in earlier, so these numbers are like similar, like whatever is the amplification in velocity control region. So we'll see same amplification in displacement control region. So what does that mean for the displacement? So if we see the solid lines, if we were like calculating displacement based on this, so that would like overestimate, and sir had said like it will result in the erroneous result. So this is how like it was giving us the displacement. But now since there is a corner period at 6 second म्हणजे dividing the velocity control region and displacement control region. So you can see after that you have like constant displacement, and that's the reason this is called as displacement control region. So this would impact on our displacement calculation and will result in the lower displacements. So the changes related to response spectrum is the corner period separating acceleration controlled and velocity control regions has been increased for the soil class C and D. And similarly for the corner period between the velocity control and displacement control for same soil class has been also increased. Then displacement control region has been now introduced, and the uh, design response spectrum up to 10 seconds, allowing better representation of long period structural response has been added. So what is the impact of this? Impact of this is like more force will see in the low rise and mid rise buildings on the site class C and D. That will the more buildings in this category, low rise and mid rise building, will approximately like 4 to 8 story building, that will fall into constant acceleration region. So what I mean is in this region we'll see more buildings since there is an increase in this period. So earlier it was like the curve was falling down here, but then since this corner period has been increased, so in the mid rise and low rise building we are expected to see higher seismic design base shear. Then the seismic forces for the building on site class C and D soils. So the acceleration and velocity control region are increased by approximately 10 to 20% respectively. Next is the next impact is the seismic force demand decreases on building with fundamental period greater than 4 seconds due to revised long period spectral shape. So here we can see beyond the 4 second for the site class A and B, and like other buildings, some more there, but then you can see beyond that period, there is a definitely decrease in the seismic demand as compared to previous. Then the last one is the design displacement and interstory drifts demands for the buildings with period exceeding 4 seconds are reduced, significantly reduced. The higher the period, the higher is the reduction in the demand. So next is the response reduction factors. So in the response reduction factors, so more or less it is like same, but then there are some cases in steel buildings where there is a reduction in the response reduction factor. Earlier it was 4, now it has been reduced to 3. Then in the reinforced concrete buildings, for buildings with ductile shear walls, so earlier there was a response reduction factor of 4, but now that has been classified into 2 categories. The category 1 is like special structured walls with no boundary elements. So for that, response reduction factor is 4.5. Earlier it was 4. And the one more category is there, the where we are going to provide boundary elements. So design and detailing of these, both the things we'll have to do as per 13920 part 5. So if we have boundary elements, then our response reduction factor would be 5. Earlier it was 4. Then earlier there was the 5 response reduction factor for the reinforced concrete buildings with moment frames and structural walls. So that has been reduced to 4 if you have structural shear walls with no boundary elements. So that has been reduced to 4 from 5. And if we have a structural shear wall with boundary elements and SMRF, so then we have that factor as a 4.5. And this is the new category introduced, that is structural shear walls with boundary elements for SMRF. And this is what is the difference between this one and this one is there are some special conditions that we'll have to meet. So then after that we can use a response reduction factor of 5. Now coming to the minimum base shear. So in minimum base shear, we know there were like some specified values for each zone. And since this was unfactored, so I have factored it. So I have multiplied it by 1.5. So these are the numbers 1.05, 1.65, 2.4, and 3.6%. This is based on the old version. In the new version, so now this has been defined in terms of zone factor, importance factor, and response reduction factor. So now this is tied to the type of structure you are using, and in any case, it should not be less than 1.5. So if we compare this, let's say we take a building category normal, and the corresponding return period in new version is 475. You can see there is a increase in the minimum base shear. So if we take, and these are the different structural system that is permissible as per IS 1893 part 5. So for these systems earlier, let's say if we are in zone 2 and our factored minimum base shear was 1.05. So now it has been revised to 1.5, and similarly for other version, other zones also we can see the change here you can see the maximum change in zone 2 like goes to 43 to like 49%, and in some cases we might see some reduction also, but then maximum change is in like zone 4 for SMRF spatial structural walls with no boundary limits. So that has been increased to 116%. So similarly, we can see for the important structures. So for important structures, also like for zone 2 change is similar, and the maximum change is like 62% for SMRF plus spatial structural wall with the boundary elements. Sorry, so there is one more, the with no boundary elements, it is 82.5%. Similarly, for critical structures, we can find this in critical structure, only 3 structural systems are allowed it, like are permissible, that is dual structural system, SMRF plus SFW with boundary element and without boundary element. So the maximum change or increase in the base shear is like around 137%. So what is the impact of this? So the impact of this is like tall or flexible buildings are prevented from having unrealistic low base shear by using by doing this change, and some of the buildings may experience increased member forces and reinforcement demand due to this. Then estimation of the horizontal base shear. So horizontal base shear, we know earlier we used to do like Z by 2 into SA by G divided by R by I and the weight. So this equation we were using, the Z by 2 was like converting this Z to the design basics earthquake, that is corresponding to 475 years. But now change is like we are using Z, and this Z is corresponding to zone factor, uh, which is for your category of structure, and there it is for the different return period. So change here is like from 475 year, and using the importance factor and response reduction factor, we were calculating this. But now here for the different return periods, we are calculating the base shear. So let's take some example. So where like design horizontal base shear for like a typical low-rise building, where residential building where height is less than 50 meter. So here the response reduction factor was 4, and the ductile shear wall was being used. So now if we use the similar wall, that is special structural wall with boundary element, so we are getting a more response reduction factor. But remember, there is a penalty for this. We'll have to use the spatial detailing specified in the 13920. So that code is like coming soon. So if we use this, so in that case, so zone 2, 3, 4, and 5, the importance factor, considering this, because building will definitely house more than like 200 people. So importance factor is 1.2. Response reduction factor is 4, and the site class was uh, type 1, and the load factor 1.5. And this building has like wide plan area, so it was like falling into the uh, acceleration control region. And if we calculate the base shear percentage, so this is 5.629, 13.5, and 20. 0.25 for the zones 2, 3, 4, and 5 respectively. This was for the earlier version. If we do this for the new version, so then obviously we'll have to use a return period corresponding to whatever category we are selecting. So this was the important category. So 975-year return period, and since there is no importance factor for the RC buildings, it is 1 for all, and the response reduction is 5, and the site class is C. Then we are not using load factor. Now it is 1, and the building period is same since it is in acceleration control region. So the change is here. There is a reduction in force for the class zone 2 and 3 and 5. And for zone 4, it is increased slightly. Why this is happening? Because there is a increase in response reduction factor. So if we use same example, if it is, let's say, low rise commercial building or any shopping mall or any important structure, hospital of that kind. So if we use that, so that would be important structure as per IS 1893/2016. And if we calculate the forces accordingly, then we'll get like 7%, 11%, 16%, and 25% base shear. And if you see based on the old code, there was a change in importance factor, but then based on new code, there is no change. Like this is same as like earlier version. So means this version. So here there is a further reduction in the base shear, and this is only the base shear calculations. Then next is like, let's say if we take a typical mid-rise building, which will be between 50 to 100 meter, and similar structural system like ductile shear walls and shear walls, special shear walls with boundary elements. If we use this, and again, this is like a mm, normal, important category. So where like a return period would be 975 years. So, and the response reduction factor is 5. So we can see here, so there is a increase in base shear up to like 55% in zone 4 and 33% in zone 2. If we take another example where like there is a typical high-rise building that is height greater than 120. So there allowable structural system in the 25 version is SMRF plus SSW with boundary elements, and corresponding system in the 2016 version is SMRS plus ductile shear wall. So the response reduction factor for these categories means both the categories in 2016 and 25 is same, that is 5. So with that, you can see here in the lower with like earlier version like 2016 version, this is governed by now the minimum base shear requirement. So this is 1.05, 1.65, 2.4, and 3.6%. And if we calculate corresponding base shear as per 2025 version, you can find here also you will get uh, in the zone 2 and 3 minimum base shear which is governing. In other cases like actual base shear governs, and change in zone 5 is like increase is like close to 79%, and in zone 4 it is 28%. In zone 3 it is around 26%, and zone 2 it is like close to 43%. So this is the example. So this is again the real buildings, and for the real buildings, so that was already designed by 2016 version, and if we calculate base share for this building using the 2025 version, this was the change. And whatever we have discussed, the whatever base share we have calculated this one, so that is only the for the whatever code gives for the uh, calculating base share. But then beyond that, like you have like overstrength load combination and other things, so that has not been considered here. So if we consider that, then our like base share is like going to further increase. So we'll see later for if we use overstrength factor for these, we will take same example. And for same example, if we use that, then what is the demand increase for the overstrain factors using overstrain factors. So this was the related to horizontal earthquakes. So if we consider the vertical earthquake, so in vertical earthquake, if we see like 2016 version, so where we should use vertical earthquakes or it should be considered, it was like in seismic zone 4 and 5. If our plan has vertical or plan irregularities, if we are our structure is resting on soft soil, or structure has long span, or structure has a large horizontal cantilever, or if we are using like pre-stressed structure or pre-stressed member. So these were the requirement where we need to use the vertical earthquake. But with this recent version, so now we'll have to use this in all zones where we have structures with large span beams and slabs, where stability is the criteria, where we have pre-stressed horizontal members and cantilevered members and gravity structures. This means like gravity structures means like we'll have to use it for all the buildings. So because all the buildings are primarily designed for the gravity load. So in all the buildings, we'll have to use in all the buildings and all the zones, we'll have to use this vertical component of earthquake. So how this vertical component of earthquake was calculated in the earlier version, where like there was a one equation where 2/3 of z by 2 into 2.5. So it was considered that like, and you will also agree that in vertical, if structure vibrate in vertical direction, gravity direction, so it will be very steep and it will more or less fall into the acceleration control region of the response spectrum, that flat region. So wherein the maximum component is the maximum amplitude is 2.5 and then divided by R by I. So with this for buildings, we used to calculate this. But if we use the latest version to calculate it, so we'll have to calculate delta V corresponding to vertical period of our structure. And this delta V, you can see for the period less than 0.01 second, it is 0.8. And for period greater than 0.1, it is 0.67. And if it is our structure falls into in between, then we'll have to use this interpolation to get the uh, delta V. So this was for site class A and B. So similarly, we can have it for site C and site D. So these factors, you can see this is like varying, like for site C, it is 0.82, and for site D, it is 0.85. For the periods greater than 0.1 seconds, in all the three cases, it is constant. So there is uh, no change beyond the 0.67, beyond the 0.1 second period. So once we get this, we'll have to again calculate the these this is called as A and V for the vertical earthquake. So using this equation, we have to calculate it. So whatever is our vertical period of structure. So again, since it is very steep, so our structure will be always like very close to 0.1, and so we will be close to like 2.5 amplitude only. So in this version, like 2025 version, what we have to do is like Z into I into A and V into weight. So here you can notice that here in earlier version there was response reduction factor. So that response reduction factor was the error. So that's the reason they have removed it. Now we have to use it. That means our whatever force we were calculating, it is now got amplified by the uh, R factor. So let's see what is the impact on our structure. So again, like the solid line indicates the as per the revised code 2025 version, and this is for the dotted lines are for the old version. So here you can see since it was dependent on the site class, dependent on the response reduction factor. So I have considered ductile shear walls uh, uh, and SMRF or SMRF plus ductile RC walls. So for these two structural system, this factor has been plotted. So you can see the earlier, since there was like only one flat number was there. So 2.5, the amplitude we were considering. So that this was like constant. So you can see across the all period range, it was constant. But here, since it is now, there is a reduction in the, means there is no denominator like R here. And this Z will corresponding to return period of your category. So you can see this. So there is a significant increase in the vertical component of earthquake. So if we, since our period range of interest would be like close to like 0.1 second. So let's see like zoomed version. So where we can see here based on old code for the SMRF and SMRFs with ductile RC structural walls, we were getting like close to 7.2%. And for the ductile RC walls, we were getting 9% component, 9% of the weight. So now here we can see if our structure falls less than 0.1 second in the like vertical period of the structure is less than 0.1 second. So you can see like there is close to 23%, minimum 23% will have to consider as the vertical component. And if our period is like more than 0.1 second, so then it is like 47%. So there is a significant increase in the vertical component of earthquake. And the what load combinations we'll have to see or we'll have to use for design this. And this is mainly going to affect the gravity element design. So where like we'll have to use these combinations. Uh, we are using this uh, like we have to design for like 1.5 times dead load plus live load that is there. In addition to that, we'll have to use this 1.2 times dead load plus 1.2 times live load plus or minus earthquake in vertical directions. So in earthquake in vertical directions was like let's say the maximum is like 47% and minimum is 23%. So here it will be 0.43 times the seismic mass. So that much additional load will be coming on our structure. And this is going to impact our design of gravity elements significantly. So next is the torsion. So in the torsion, in 2016 version, so it the building is said to be torsionally irregular with the maximum horizontal displacement of any floor in the direction of lateral force at one end of floor is more than 1.5 times of the minimum horizontal displacement at the far end of the same floor in that direction. That means delta max by delta minimum, if it is greater than 1.5, and if your natural period corresponding to torsion is uh, more than those of first two translation period, that is translation in uh, two directional horizontal directions. If it is that there, then our structure is said to be torsionally irregular. And if it is torsionally irregular, then we'll have to use this if our delta average is in between the 1.2 times to 1.4 times of delta minimum, then we could have used the response spectrum analysis, three-dimensional analysis, that is the response spectrum analysis we could have used. And beyond that, like if it is more than, it is delta max is greater than 1.4 times. If it is there, then it is going to be uh, not acceptable, and we'll have to use the or use the different structural configuration. We have to adjust configuration. That was the requirement as the old code. But as per new code, there are two criteria. One criteria is building period, the torsional period should be less than first two translation periods. So if it is there and your psi is greater than 0.4, then you are not, and again, they are using torsional flexibility as term instead of torsional irregular. So if you are not meeting any of this criteria or both the uh, criteria, then you are not torsionally flexible. If any of the criteria is torsionally meeting this, then you are torsionally flexible. So buildings with torsional flexibility are not permitted. So now code is clearly specifying the beyond the 50 meter, this code is not applicable. But then in that case, we don't have any guidance on like how we should consider torsion in the buildings above 50 meter, because after 3rd May, so this code is not like 2016 version is not like applicable. You will have to use 2025, and then there are many buildings beyond 50 meter, like where we can we'll have to check this torsion, whether structure torsionally flexible or not. So I think that needs to be addressed. The second part in torsion is like design eccentricity. So design eccentricity is like how it was being used in the analysis was for the it was uh, considered as EDI is equal to 1.5 times the static eccentricity plus or minus 0.05 into width of the structure. So this was being used for the response spectrum analysis as well as equivalent static methods. But now if we see in this like equivalent static method, this factor from 1.5 to 1.8 has been revised from 1.5 to 1.8, both for the equivalent static method and response vector method, and the for response history method, it is not amplified. If we take a look at the different codes and how they are doing, so in the 2025 version for the equivalent static method and response vector method, it is 1.8. Earlier it was 1.5, and then earlier criteria was like delta max by delta minimum is greater than 1.5, and your torsional period by your translation period ratio should be greater than 1. So that was the criteria. Now that criteria has been revised to like your torsional period should be greater than translation period plus the psi is greater than 0.4. If we see other codes for ELF, that amplification factor for Iran for ELF, it was 1 to 3. It is 1 to 3, and for response spectrum analysis, it is not there. So if we see the all the codes except India, there is no dynamic amplification factor for the response spectrum analysis method. However, there are some dynamic amplification. There is some way to amplify that in like Iran, USA, and Turkey code for the equivalent static method. So I am not sure like why we are considering this. And it has like a significant impact on our design. So in our buildings we have seen, so from changing this factor, like considering this factor is like increasing forces, especially in the age of the building by like 5 to 15%. So the impact of this overall is like higher torsional amplification that will going to increase our shear moment, axial forces in our edge columns and shear wall. The floor diaphragms and collectors for the diaphragm design, they will have to design for the enhanced in-plane shear and torsional force. Then building corner will experience the larger displacement, and drift will be more critical in that area, and where we have like plan irregular and the stiffness eccentric structures that will going to attract like higher torsional penalties. Uh, then the foundation for the uh, elements at the corner, so they are going to see like higher overturning and axial forces due to this amplified forces, amplified torsion, and we'll have to be very careful while selecting our structure. So it should be like symmetric layout and very balanced in stiffness, so that like we have a lesser static eccentricity, and so there will be less amplification of that. We have to maintain that. Then the load combinations. So in the load combinations, earlier we used to use like 1.2 times dead load plus 1.2 times live load and plus or minus earthquake load there. And again, there is like variation in this like X, Y component also and Z component also we can combine in this. And the other combination was like 1.5 times the dead load and plus or minus. Sorry, here it is typo. It is like 1.2 times earthquake, uh, and here it would be 1.5 times earthquake, like 1.5 times dead load plus or minus 1.5 times earthquake load. And here 0.9 times dead load plus or minus 1.5 times the earthquake load. So if we consider the current code, so we can clearly see there is a no load factor in this. the combination are like same, except there is a no load factor because we have already amplified the zone factor to consider that. In addition to that, there is a additional load combination, and that will have to use. So that additional load combination is uh, dead load plus live load plus or minus omega times the earthquake load. So omega is the overstrain factor, and what is the impact of this? So, and where it is applicable. So where we'll have to consider this factor. So the load combination, that is additional load combination, that needs to be considered in the design of the members in concrete building. And that overstrength will be overstrength factor will be 2. So which concrete buildings? The columns in the buildings with SMRF, then beam to column and beam to wall joints, which are part of SMRF and uh, special structural shear walls, uh, and the structural members of foundations. So SMRF columns, beam column joints, and beam wall joints of SMRF and special structural walls and foundation. This needs to be designed for the overstrain factor of 2. So our uh, load combination would be here dead load plus uh, live load plus or minus 2 times the earthquake load. So that will be for this, like foundation, column, beam and wall joints, and in the SMRF and SSW, and columns in SMRF. So we'll have to design for the twice the demand that we got from the equation. So, and this needs to be designed for flexural as well as shear. However, for the structural shear walls, we'll have to design only for the shear. So this omega is ranging between 3 to 2. And this is depends on the height of the wall to the length of wall ratio. If you have long walls, then that factor would be 3. And if you have like squat wall, so then factor is 2. And if it is between the long wall and squat wall, so we can use we can use 2.5. So here only in the shear wall, we'll have to only design for the shear and not for the flexure. So let's say if we check the what is the impact of this on the overstrain using overstrain factor, like what is the increase in base shear percentage. So the same buildings that we have checked for the uh, what is the variation in the base shear. So same building, what we have done is like the force for the design of shear wall, that is in shear only, and the foundation. So here there is for the shear wall, special structural shear walls, the factor of 3, overstrain factor of 3 has been used. And for the foundation, it has been used as 2. So the base shear demand for the shear wall for shear design has been increased up to like 211% for the uh, zone 4, and for zone 2 it is 167%, and the foundation demand is like increased 107% in zone 4 and like 78% in zone 2. So there is a significant increase in the demand for, like, if you are designing shear walls like spatial structural shear walls, then there is a significant increase in the shears. So if we take like another example where like typical low-rise commercial building, height less than 50 meter, you can see the increase in like shear demand for the shear wall is like close to 149%, and the minimum it is like 113%. And in foundation, you can see in foundation design, that is up to like 66%, and 42% is the minimum. If we see the typical mid-rise building, so its height ranging between 50 to 100 meter. So you can see that demand is like going as high as like 366% in the zone 4, and like in zone 2 that demand is 300%. That is the minimum. If we see the foundation design demand, so maximum is at 211%, and in zone 4, and like minimum is 167% in zone 2. If we see like high-rise building with height greater than 120 meter, you can see the demand is like going for 65% in zone 4, and 329% in like zone 2. And if for foundation design, that demand is going up to 277% in zone 4, and zone 2 it is 186%. So there is a significant change in the, or significant increase in the demand for the shear wall design as well as foundation design. And this is only the shear demand. So for foundation design and shear wall design, whatever is the overturning demand, so that will we can see in the model when we model it. So the change is like overstrain factor for shear force design of special structural wall has been introduced, and foundations to be designed for overstrain factor of 2. So what is the impact of this on the walls? The thicker walls, heavier shear reinforcement, and we need to have like stronger boundary element since there is a increase in shear force demand. So in coupling beams also, we'll need larger beam sections, or if not, then we'll have to provide the diagonal reinforcement, steel plate or steel section to meet the higher demand. And the impact of foundation, impact on foundation is like we'll have to provide larger foundation size and higher reinforcement. So then story drift. So story drift, there is no change in the story drift. So whatever limits was earlier there in the code, that is also like same for all zones. That is 0.4%. And what combinations we are going to use to check the drift is like 1.2 times dead load plus 1.2 times live load plus or minus earthquake design earthquake forces. And other combination is 1.5 times dead load plus or minus earthquake load, and 0.9 times dead load plus or minus earthquake load. So when like we are using response spectrum method or response history method, then we need not to amplify the displacement response. That is like VB bar by VB correction, and there are other requirements specified in the 8.3.3.2 E4 and 8.3.3.3 D4 of the IS 1893 Part 1 and Part 1. So with this, like we can see some case studies. So let's see first, like office building, short office building, what is the impact on the short office building? So this is the building that is located in the NCR, and the building configuration is like 4 basement plus ground plus 18 floors. The building footprint is 60 meter wide in like X direction and 95 meter in the Y direction, and height of building above foundation is 100 meter, and height of building above ground is 80 meter, and typical story height is 4.2 meter, and typical basement height is 4.8 meter. So the structural system used in the both the cases in 2016 and 25 version. So ductile walls were used, and the zone there is a no change in zone. Earlier version also and this version also, that is the zone is like 4. And the importance factor for 2016 version is 1.2, and as per new version is 1. So this site, like earlier geotechnical investigation was done, and that time the site class or was like soil type was type 1 hard soil. But then when we do the shear wave velocity uh, uh, test, then the site is now in the site class C. And the response reduction factor in the earlier version, it was 4, and now it is 5. And the zone factor corresponding to 2475 years or MC level, that was 0.24. And zone factor now corresponding to like 975 years, since this is fall into important category of structure, so it is like 0.28. And the overstrain factor for slender wall design, that only for the shear, that has been used 3, and the overstrain factor for squat wall, again for shear only, that is 2, and overstrain factor for foundation design, flexure and shear, that has been like is again used as 2. So the time period calculation, since the height of building is more than 50 meters, so here this time period uh, as per IS 16700 has been used. So that time period is coming 1.79, and the height for this was considered 80 meter above the ground. So if we see the factored base shears, if we uh, see, as per the IS 16700 version, the minimum base shear requirement was 2.4%. And if we calculate that as per IS 1893 2016 version, and as per site investigation, our site class was type 1. So for that, the base shear was 3%. If we consider the medium soil type, then that base shear was like 4.1% in the both the direction X and Y direction. If we consider the latest version, so then base shear demand was 4.7%. And then if we consider the shear demand for the shear wall design, so it was like 14.1%. And the wind forces on this building was like 0.8% in X direction and 1.35% in the Y direction. So our building was like clearly governed by earthquake, even in the earlier version of code also. And if we see the demand increase is like seismic forces as per IS 1893 2025 site class C are about like 55% higher as compared to type 1 soil of 2016 version. If we consider like type 2 soil of 2016 version, so we were like around like 15% higher in the current code. So the due to introduction of overstrain factor for wall design, shear design of the wall, the shear demand on the RC wall is like increased close to like 400%. That means 5 times the as compared to the 2016 version of the code. Then if we see the demand, so the walls has been like designed for the for shear design. So it has been designed for like close to like 300 uh, mega Newton force with overstrain factor of 3, and like overstrain factor you can see for the foundation design, these with overstrain factor of 2. So it is designed like for the close to 9 giganewton meter overturning moment. So with this, so on the left side, you can see the 2025 version wall sizes, and on the right side, you can see like 1893 2016 wall sizes. So there is a significant increase in the wall thicknesses. We can see like zoomed version of the core. So here we can see earlier this wall size as per like old code, it was like 600, and now we need like 1800 thick walls. Though these walls were like 450, now it has been increased to 1200. And these vertical walls, like this wall were like on the periphery of the core, that was 450. So now they are like 1000 thick. And these walls earlier it was like 600, and this is now 1800. So the earlier requirement in the y direction, so percentage of area was like 1%, and in x direction it was like 0.9%. So now that has been revised to like 2.6%. So this is the impact of like uh, design with overstrain factor and increased forces. So whatever we had discussed earlier, so we had considered one part, let's say zone factor, and then soil, and then minimum base shear, and the just base shear. So that was like we were considering the impact of like one component, like what is it? But then this is the overall uh, and also design. So there is a significant impact on the wall sizes. So we can take like one more example of tall residential building. So again, this building is in NCR, and the building footprint is like 52 meter in X direction, and 26 meter in Y direction. And the building height above foundation is 192 meter, and building height above ground is like 180 meter, and typical story height is 3.4 meter. So here the structural system used was ductile walls plus special moment resisting frames, and seismic zone was 4, and again like importance factor for 16 it was 1.2, and 2025 it is 1. And again like here as per earlier geotechnical investigation based on SPT value, the site class was type 1, and after doing like shear wave velocity test, so it is found to be like site class C. And the response reduction factor, there is no change, it's same. And the zone factor again, like same as like previous project. And return period is like again same 975 years. And these overstrain factor for slender and squat walls are like 3 and 2 respectively. And that is for shear only. And the overstrain factor for foundation design, flexure and shear, that is 2. So here also the time period has been calculated as per the IS 16700 2023 version, and the height above the building, ground floor is considered as 180 meters, and the corresponding time period was 3.3 seconds. So here, the minimum base shear as per 23 version of 16700 is like 2%, and for the hard soil of 2016 version, it is 1.3. And for medium soil, it is 1.77%. And with the current or revised version of IS 1893, it is 2.54. And the overturning, with the overstrain factor for the shear wall, the slender shear walls with overstrain factor of 3, that demand is like 7.62%. And here we can see in the earlier version, the building in Y direction was governed by the wind. And in X direction, it was governed by earthquake. But now with this, now building is governed by earthquake in both the directions. So wind to seismic moment ratio with factor forces is like 0.67 in X direction and 1.22% in Y direction. This is as per 2016 code version. And it is 0.53 in X direction and 0.98 in Y direction with the 2025 code. So building is wind governed in Y direction. So it is governed in the overturning moment. So with overstrain factor of 2, the foundation per 2025 code. So that is like 0.26 in X direction and 0.49 in Y direction. So here we already had higher wind overturning moment. So this is not governed by the foundation is not governed by the seismic in the overturning. So seismic forces as per like 2025 version soil class C, they are about 95% higher for the type 1 soil of 2016 code, and it is 45% higher for the medium soil of 2016 version. And due to overstrain factor for wall shear design, shear demand on RC wall has been increased by 200%. That is the 3 times the original demand. And here, if we see the earlier uh, size required as per code, it was like 500, and now it is 850. So since building was governed by wind in Y direction, so there is no change in the Y direction. So the wall sizes was already higher to meet the wind requirement. So the wall required as per 2016 version plus wind, it was close to 6.5%. And this is due to there was some like drip related issue in this building. So and we had to like increase the sizes. And here with this in the X direction, the requirement has been revised to 8.2%. So that's it from my end. If you have any questions, you can put in Q&A tab. And thank you. So I think we are now open for the questions.
Yes, thank you, Dr. Vijay Khose, for very informative, very excellent presentation, very detailed analysis of all the clauses and the impact on the design, and also a very good comparative study. So we start with questions. Will the model be separately for RCC beams, RCC columns, and RCC shear walls and RCC footings?
Can you elaborate that? So
Yeah, actually, the question is like that. I don't think so. The load combinations will change, and you'll have to use it for
yeah, you can
different
have,
element design.
I
Yeah.
think, same model, and even for the members which are taking lateral loads, for that also you will have to design for the. I think this question is related to vertical earthquake component. So there will have to use same combinations, load combination for
Yeah, I think.
all the elements, vertical as well as lateral. Sorry, gravity as well as lateral elements.
Yeah, and along with that, you will have few more load combinations for to satisfy the overstrength design clauses.
Yeah,
So
yeah.
those will be applicable to only certain elements.
Yeah,
So
that will be only for the lateral elements. So we can have a same model, and in that model we can have a different load combinations. And whenever you are designing that particular element, you can use that combination.
But
So there is one.
directly using that combination may be problematic, no? Because what you are interested in shear wall design is only for shear, correct? Overstrain factor.
Yes,
That
yes.
shear will also induce additional moments, that additional shear. So
No, so
those are not to be considered, correct?
yeah, so that you will
Hmm.
when you are designing for shear, code is
Hmm.
specifically saying like design for shear. So
Correct.
in that case, you will have to design like generally we take these forces and we design the elements outside,
Outside,
not
yeah,
in
that's what
that. But then you are right. Like if you have like in ETABS, then you
ETAP,
will
yeah,
have to have a like separate model in that
Yeah,
case.
yeah.
separate model
I
for
think,
the.
I think
for us.
unless like
Hmm.
ETABS comes up with something,
Hmm.
otherwise it will also consider moments. So you will have to design outside, not in
Out,
ETABS. It is not possible in
yeah,
ETABS because it
yeah,
will consider that component as well.
correct.
Absolutely right.
Yeah.
So uh, you have already clarified, but I received one question on my on a WhatsApp message. Do we need to design all columns, all shear walls, and all foundations for overstrength?
Yeah, so code is clearly saying like spatial structural shear walls needs to be designed for the overstrength for the, and they have provided the range between like sorry 3 2.5 and 2, so that you will have to design. And for the like columns, if that is in SMRF, and then the beam column joints and the connections of that SSW, that is special structural walls, and the SMRF. So that needs to be designed for the overstrength factor of 2, including the foundation. So I think where to use it, like that is very clearly stated in the code.
No, but the shear walls will be designed only for shear design, not the
Yes,
flexure
that's
design, right?
Hmm.
not flexure design.
And do we have to design the foundations for all the shear walls
Yeah,
with the most strength?
all the foundations will have to design for the overstrength factor of 2.
Okay, fine.
So what about the
Just
shear
one more
walls?
thing to add here. Not only the structural design will be done with overstrength, the geotechnical design will also be done with overstrength. This is important.
Right.
And stability checks also, correct?
No, it's only the strength part.
No, so stability checks, we
Stability,
don't
you
need.
mean overall?
Overturning or sliding, whatever it is, overall.
No, there it will not be required because this is
Because that is not the force, actually.
Yeah,
That's the capacity that you are designing for.
Okay.
Okay, so one more question. Mm, For footing sizes, along with factored base shear, we have to consider additional overstrength factor, whereas as per 2016, footing sizes are from unfactored load combination. No, it is not for the sizing, it is for the strength of the foundation.
Perhaps
The question is that
the question
do
is
we
perhaps
need
related
to...
with the geotechnical design. So sizing of the foundation comes from the geotechnical design.
Right.
Geotechnical design is working stress method, and in the previous code we were using unfactored load for working stress. The question is that now how the sizing will be done. So the sizing now will be done either using the return periods corresponding to working stress combination, or another possibility is that we use return periods of limit state and divide it by 1.5. Forces we reduce by 1.5. So code is not very clear, but it appears because it has given separate load return periods for working stress load combinations. So those return periods are to be used for geotechnical design. The EL in geotechnical design and the EL in strength design will be different.
I think it is already answered. In column and column beam wall junction, also we need to introduce overstrength factor. For that, why we did not show in design change, why only shown in shear wall and footing? This question is not clear. We'll move to another question. Is there any cost comparison available for your case study? What was the impact with respect to the 2016 code?
Yeah, so the cost is like, again, it depends on the configuration of structure, but then the impact was like around like 40%.
Okay. It will vary from building to building.
Yeah.
Cost increase because of this 2025 code.
Yes.
Structural cost.
Yeah, so this is again like structural cost, but then with this there is loss of area also, and the if that is a commercial building, then in commercial building there is also loss of revenue with that.
Okay.
I think this question is already answered. Is the overstrength formula is to be used for foundation sizing also?
Yes.
I think it is for the design of shear and flexure, because the sizing will depend on geotechnical aspects, mainly the bearing capacity.
Not get, is that question or clarification?
No. I'm trying to clarify. The question is whether the overstrength combinations are to be used for working out the foundation sizes as well.
Yes, actually the objective is that foundation should be stronger than the supported element, beam, column or shear wall. So when we have to make it stronger, we have to make it stronger structurally as well as geotechnically. So both the capacities are to be increased by this overstrength.
Okay.
Okay, Arvind, can you take up
Yeah.
other questions?
Yeah. Next, since the provision of boundary elements is governed by IS 13920 and is not directly under the control of design engineer, means what he meant to say is there will be boundary zones are often curtailed at upper stories based on extreme fiber stress limits in the wall. In such cases, what response reduction factor should be adopted for those upper portions of the building or where plastering changes are not expected? But since there is a different response reduction factor for providing boundary element, this question arises.
Yeah, so response reduction factor which will be applicable will depend upon the plastic hinge region. So in case of shear wall, if capacity design is properly followed, then the plastic hinges will form in the base. In the bottom stories, boundary element is required and response reduction factor will be used accordingly. In upper stories, it may not be required. But the capacity moment diagram, like that provision is not there in our code. So it should be ensured that the plastic hinge will not form in upper stories. So upper stories will be designed for a modified bending moment diagram, which is given in ACI 318. It should be designed for that, and it should be ensured that no plastic hinge will form in the upper stories.
Thank you, sir. Next question is in critical classification in zone 6, if the RCC building is only single story, in this case also why SMRF is not allowed? Means it is not related to height. That's why.
I mean, there is no theoretical or technical background for that. It is decision of the code committee. That's it. You can raise your concern. You can write to the code committee and ask this question. But currently, that is the decision of the code committee.
Yeah. Yeah, this one is important question to Dr. Vijay. This gravity structures means like dam-like structure, I think. All buildings will not be covered in that. How buildings are classified under this?
Actually, this has been like discussed with
Not Vijay, not only that. If you read the previous, I mean the top paragraph where before these are given, it is given that in following types of structure, it may be significant. It is not that only in these types of structures it is to be used. It is to be considered everywhere. But in these structures, this may be significant. It is not saying that it is to be considered in these type of structures.
But when you say gravity structures, all structures are covered. Then
Yeah,
why other categories are given then?
Yeah, so
Logically,
actually, there is a ambiguity in this, and this has been like discussed like when there was like with the committee members, some of the committee members, and they have clarified like we'll further clarify it, and before the implementation of this code, there will be amendment to
they
this.
will consider it as a dam structure, correct?
No. So it is for like all gravity structures. We'll have to do that.
But logically, then other structures need not be defined. No? You can directly say it is all for all structures. Because all structures are anyway gravity structures.
Yeah, so that we have discussed with them, and they said like there will be amendment coming in before 3rd May.
Okay. Next is practically how vertical time period is calculated.
So you can calculate, in ETABS. It
No,
provides.
I mean, it is to be calculated using the eigenvalue solution only. So same method, modal analysis, which you do, it can be done using that only. But if the frequency corresponding to that is very high, okay, it is this period is very short, the structure is very rigid in vertical direction. It becomes very difficult to solve eigen problem to that. And those methods which we are using, sometimes those do not yield that. So that is the problem. And we know that most probably it is going to be less than 0.4 second, close to 0.1 second as Vijay has shown. So SAYG value will be 2.5. So what is the point in going into so much mathematical details? That's why it is considered.
I think that was the thought process in last version, and that's why there was like they have considered 2.5 like one value.
Yeah, this also it is 2.5 now in vertical direction for building.
Yeah, this is 2.5, but then there was like only one value. Now we have a full response vector for that and using that, like, but then it cannot, I think it will not go beyond, like it will be around 0.1, 0.2 second and not beyond that. So again, it will fall into that only 2.5.
Okay.
And moreover, in vertical direction, it will be always static analysis. It is
Yeah.
not going to be dynamic analysis. We have to understand until unless we are using time history, vertical time history.
Thank you, sir. Next is in calculation of H for time period calculations. For stepped building, which was there in earlier code, is now removed. There is a question mark. Stepped buildings, what was there in earlier code?
Stepped buildings.
Maybe.
Not clear.
I don't
What is the
think.
question?
In calculation of H for time period calculation, H that is height. For step buildings, which was there in earlier code, is now removed.
Okay.
I think so. It is not there.
Standard building, it is not there. It is there, I think. They have even shown that shear walls are to be provided. Those things are there. It is there for H calculation.
Okay.
Or step building perhaps means where the cross-sectional area was changing and
Changing, correct. I think that.
Plan area changes as
plan
per the
area
height.
is changing. That is meant by step building. Okay, yes, because that was very confusing. That was not working. It was working wrong in many cases.
So it's not there now.
It's not there.
Next is in the case of time period in vertical direction, is it not that the time period has to be for the component, for example, that for a large span beam, it is well known that the large span beams will have more time period and hence less seismic force. So in vertical direction, one has to consider only the vertical time period of the critical component and not that of the entire building.
See, if you are designing a component, for example, if you want to design a beam under a vertical earthquake force, then you will consider period of beam. But when you are designing a building means mainly designing columns. So that when you are designing columns, you have to consider the period of the structure as a whole. It will not be just the beams.
Thank you, sir. Next question is how beam column joints overstrain factor can be addressed in design? Joint designs.
That's a little difficult. What I have thought of that you have to calculate because let me give a little background also here. In calculation of joint shear, you need the axial force in beam bars which are embedded into the joints. So ultimate we can calculate by taking 1.25 F by ST. But here we have to calculate the applied stress, the stress under applied loads. So for that, we have to perform a section analysis. We have to calculate the stress in the bars, which will be less than Fy. And then that stress is to be multiplied by the factor. And then the shear stress should be calculated for that amplified force in the longitudinal bars of the beam, which are embedded into the beam column joint.
Okay. Thank you, sir. That was very much required. The explanation is very critical. Next is in zone 4 for important building. This is for Dr. Vijay. In zone 4 for important building, SSW plus SMRF system to be used, but you have considered only SSW, whether it is allowed. In your example, I think what he is referring to.
Zone Four.
For important building, I think your second example.
Yeah, so let's take next question. I will check.
Yeah,
And yeah.
okay, thank you.
Okay, I'll take this question.
Yeah.
In the term definition for liquefaction potential, item 3.23, it is pertaining to partially saturated cohesion-less soils. However, in section 9.2, procedure for evaluating cyclic ratio for clays and stilts, uh, silts are also included. Does it mean that code now requires clays to be assessed for liquefaction?
Yes, in certain types of clays where sandy content is there and silts, this can happen. So that's why it is required.
What would be the overstrength factor for design of foundations? Will it be different for columns and shear walls?
It will be different because overstrength factor depends upon the component which is supported by the foundation. So actually it is the overstrength in the supported component, not of the foundation itself. Foundation will be designed for it. So it will depend which member is supported on it. So it will be different for column and shear walls.
Okay, Arvind, you can take up.
Yeah,
Next question.
thank you. The new code more strict and seems to increase the design demands and higher structural costs substantially. As a company, are we finding performance-based design to be the best way to keep projects economical? Or you any optimization strategy, different optimization strategy will be there?
But performance-based design is not allowed to bypass any of the code clauses. Performance-based design you can use to improve the performance further.
Okay.
But you can't compromise on performance by bypassing any of these rules. So these have to be followed in any case. Performance-based design will be over and above these two.
Yeah,
Next.
so
Dr.
I
Vijay,
can.
you want to show
Yeah,
something?
so you can see in zone 4 also, like in all the categories, you can use ductile shear walls.
Yeah.
This is in like table 13.
Yeah, it is there. It is there.
Yeah.
Thank you. In the comparison of building base shear design, stroke design, earlier model, what was the boundary conditions assumed? Is it fixed or springs are used? If it is fixed, then will the base forces like moment may be higher than that considered with springs?
Can you come again?
Yeah, in the comparison whenever with 2016 and 25,
Mhm.
what were the boundary conditions assumed? Is it fixed or springs are used below raft?
No. So no spring has been used in that.
So if it is fixed, then will the base forces like moment may be higher than that considered with springs? Means whether providing springs will be advantageous or any expected difference is expected.
Providing spring will make your structure flexible. So it has like other considerations. So like we are like yet to check with like spring what is the impact. But I think the foundation forces might be less in that case. But then your flexibility, like you will have to satisfy the drift criteria. So that criteria satisfying will again like lead to some other complications.
But in acceleration control region, it may help, no?
It depends. I think we'll have to do some like case studies and then only I can like comment on that.
Okay. Thank you.
Okay.
Because that is like very like time consuming process, like modeling everything in the one model and then getting
right.
like those. So I think we have requested for more detailed guideline on like how to be done. Yeah.
Yeah. Anand, please.
No, how many questions we are going to take? Because now it is almost 7:25.
24. Yeah, we'll
Yeah.
take another 10 minutes, maybe 5 minutes. Probably.
Yeah.
Yeah.
You can go ahead with the questions,
Yeah.
Arvind.
Yeah.
You can take 5 more minutes because
Yeah, 5 more
7:30
minutes. 7:30 will close. So why the overstrength is only multiplied to shear and not moment in shear wall? Any logic behind that?
See, actually,
Yeah, Vijay, go ahead.
yeah. So basically, the why we have this is because like we want to meet the capacity shear criteria. So if we increase the flexure reinforcement as well, then our structure we will not ensure that there is a failure in like ductile behavior will not be ensured. To ensure that, we'll have to do only in shear. So earlier it was not clear. Then the reinforcement requirement and the size requirement was even higher. Then we discussed with the committee, and then I think they later realized, and then it has been changed only for shear.
Yeah, we want to avoid shear failure for the
Yeah.
walls.
Yeah.
Next is the basic. What is the difference between dual system and SMRA plus SSW system? That just
dual,
70%.
yeah, dual system, like you have to ensure that like
Yeah.
your moment frame is taking
At least
25%, at least 25% force. In other case, there might be case where you might not meet that criteria.
So actually both the systems are same, only the R value will change based on that. And if you want to get higher, use higher R value, then you have to ensure that the frames are taking at least 25% force.
Yeah. Yes. Yes.
Next is, sir, do we need to design the shear walls for overstrength load combinations, or just we have to check the maximum shear stress in walls will remain in limit?
No, we'll have to design. We'll have to design. So what is the point of like only checking it? If we don't have that reinforcement in the wall, then like checking will not prevent the failure of wall, right? So we'll have to provide shear reinforcement as
The
well.
shear wall, shear design for the walls will be with the overstrain factor.
Sorry, I was distracted. Is any question related to me?
No, sir. Yeah, we are just finding the correct questions. The calculation of time period, especially TH in response spectrum method, is not yet clearly elaborated right now. Now we will not able to give the stepwise procedure. Sir, shouldn't overcapacity, overstrain consideration reduce the section and reinforcement rather than increasing it? No, this is also not clear.
No, I think I can answer. This
Yeah,
is interesting
yes.
because it's a interesting thing.
Yeah.
Overstrength is considered in two ways. One is that the overstrength which is available beyond our design value. And in response reduction factor, we consider that. So response reduction factor has the effect of overstrength as well as ductility. The problem is that overstrength, if it is provided in brittle member, it is good. But if it is provided in ductile member, then it is not good. Because if I'm providing overstrength in the ductile member, then it will increase the demand on the brittle member also. So when we are designing brittle member, overstrength is disadvantageous and there the sizes will increase. When we are designing a ductile member, their overstrength is advantageous and we will reduce accordingly. So we work both ways. In case of ductile members, we reduce by overstrength, and in brittle members, we increase by overstrength. Because shear is a brittle mode, that's why when we are designing for shear, we will increase by overstrength. When we are designing for flexure, we have already reduced by overstrength factor, which is included in response reduction factor.
We'll take last question. At the moment in 13920, we have only column beam joint for distortional joint equation, but not for shear wall beam joint. So what do you do as per current code? Shear wall beam joint.
No answer at the moment. I have also to look into it. I have to think that how to calculate the shear stress or the stresses rather inside a shear wall beam joint.
Yeah.
That is yet to be seen.
We'll take this last question. In the earlier comparisons of less than 50 meter height building, the base shear forces were lesser as per the new code. Time periods were same for both the codes. Is infill wall period also used for comparison?
No, it's not like only whatever period is specified, that equation, like empirical equation provided, based on that it was calculated. And the time period was 0.4 seconds. So that was in acceleration control region. And so there is no amplification in that region for the, and there was also reduction in the response reduction factor. Earlier it was 4 and it has increased to 5. So due to that also we are dividing it by 5 instead of 4. So that is also giving us the reduction in the forces.
Thank you. I think we should close all the questions in question answer sessions are documented with us. We'll try to provide answers to that through mail. I think.
So thank you. I would propose the vote of thanks. Thank you, Dr. Yogendra Singh and Dr. Vijay Kose for this enlightenment, the knowledge sharing. And I would also like to thank all participants, almost, I think, approximately, I would say 500 in numbers, for their support and involvement. And lastly, all Epicons Friends of Concrete team members for making this webinar a grand success. So thank you everybody.
Anand, I'll add one more sentence.
Yeah.
This webinar was a grand success. Total participation was 627.
Right.
Joining from 26 states and 3 union territories. Beyond that, it is interesting to see that 12 participants from 7 different countries have joined, showing the very widespread interest. Worth mentioning is 140 participants joined YouTube channel because the capacity of registration of Zoom was exceeded after 500. So for this, special thanks go to Dr. Yogendra Singh and Kose, because people have come only seeing their name. Thank you, sir.
Thank you. Thank you.
Thank you.
Thank you, Kulkarni sir. Thank you very much.
Thank you.
And thank you, Epicons, for arranging that. So a big thanks.
Thank you, sir.
Thank you.
On behalf of EFC, special thanks to all the participants for your active involvement, which made this webinar successful. My thanks to our moderator, Engineer R.N. Kulkarni and Engineer Arvind Parwaikar, our webinar convener, Engineer Jan Kulkarni, and our sponsor, Trizone MEP Solutions Private Limited, for their support. I sincerely thank our speaker, Professor Dr. Yogendra Singh and Dr. Vijay Kose, for their valuable insight on IS 1893-2025. On behalf of EFC, Epicons Friends of Concrete. This is Rashmi Zarode, webinar coordinator, signing off. Thank you and have a wonderful evening.
Shall we close?
So we close now? Yeah. Thank you.
Yeah, close. Thank you.
Thank you.